Thanks to organizers for the invite and for putting this on. It's been really good so far. Hopefully I can keep that up. And yeah, so point of this talk is to talk a bit more about fault zones and fault zone geology, geological processes, and whether that might have some control on the spectrum of slip styles and on the earthquake cycle. Obviously, like with all these other longer talks, there's lots of people to thank that have been involved with anything I've done looking at faults for the last 10, 20 years. So lots of grad students and postdocs, as well as several colleagues that will come across along the way. So if I can get this to work. All right, so what I'm planning on doing, trying to sort of keep to a similar sort of outline as others have this week. I'm going to try and start with bit of the background, bit of basic fault zone geology. Might be a repetition to a lot of you, might be a bit unusual to others, so hopefully that's useful and also puts us at sort of similar language. Some terms might be used a bit differently across different communities. Then I want to talk a bit more about fault zone heterogeneities, it's kept coming up during the week so far, so think a bit more specifically about what it is that might vary within faults. We've talked about different kind of slip. I want to look briefly at two examples. So a little bit about what happens in fluid saturated subduction zones, and the other end member, what might happen in really dry lower crust. Is it the same kind of processes? Are there some differences? And then we'll see whether there's time for some discussion at the end. Right. So, stepping back in time a little bit, fault rocks and fault mechanisms is something that geologists have described faults for a long time and tried to think about what different fault rocks might mean about mechanisms in faults for a long time. Simpson 77 kind of said a lot of what we're saying now and had this idea of that, faults are incohesive and fractured near the surface, and then as we go deeper, they get more cohesive. They start generating earthquakes. If it's dry, you might find some pseudotechylites of friction melt, and then it gets warmer and higher pressure, and we change from fracturing to flow. And along that depth transect, we change from low differential stress, it gets higher, it's at the highest around a frictional to viscous transition, and then gets weaker again. And that picture hasn't really changed dramatically. This is how we often draw it now, combining Simpson's sort of fault zone idea of fractures dominating near the surface. They might be within a fault zone. There might be more than one fault strand. As we get deeper, we start getting into more ductile rocks. Some of these fractures might propagate down into the ductile regime, and then as we get deep enough and warm enough, rocks tend to flow. Several groups, but Brace and Kolstad did this quite early in 1980, made this plot of saying, well, the reason this is happening based on experiments is that at shallow levels, frictional sliding is easy, normal stress is low. It gets harder and harder or linearly as you go deeper because normal stress increases, and at some point this curve, which represents viscous flow, that goes way out here, but then that gets easier as it gets warmer, and we have a mechanism switch. And Chris talked about this in detail yesterday. This you could think of in terms of frictional stability, that very near surface, frictional sliding tends to be stable, because again, normal stress is low, and a few material properties. Then we go deeper, rocks tend to be seismogenic, and then we go deeper again, it gets warmer, and creep is stable because it's velocity strengthening. So that's a picture that sort of mixes geology and mechanisms. Let's just look a little bit at what happens in these fault zones. What do they look like? So you've got your end member. People have talked about the San Gabriel fault a few times this week. This is the San Gabriel fault. It is a really planar, very obvious thin fracture or thin fault. You zoom in on it. It's a few centimeters thick. It's an ultracatacclasite. It's really fine-grained. It's basically ground-up rock flour. Looks a bit like what Chris shows in the lab. And it's a little bit, but not very damaged either side of it into hard country rock. So that's an end member. Another end member of really localized slip surfaces is pseudotachylite. So pseudotachylite is a friction melt. It's the one place, Christy Rowe has suggested several others, but it's the one place where everybody agrees this formed in an earthquake. It is basically a friction melt, so you slide on a localized surface, shear heating allows the rock to melt, and it might flow, and it might go into little cracks, so you see little injections. It can be localized along a plane like that, or some earthquakes clearly are more complicated because you have pseudotachylite covering multiple surfaces and fractures in between them. In examples where you don't necessarily just have localized slip on one surface, but you're dealing with something more complex in a volume. So that's the example of slip on one single surface. Faults can be more complex than that. We might have multiple slip surfaces. So here's an example from Husavik, Northern Iceland, vertical strike slip fault. You see lots of red lines that are individual slip surfaces, and it's fractured between them. So you have a damage zone on this photo that's a few tens of meters wide, but it goes on for about 2 kilometers. Fractured rock with lots of slip surfaces. That's been brought up as a way of creating permeability because the damage zones are fractured and easy for water to flow through. It can be a little bit more complex. This is the Glade Fault. It's a dead strand of the Alpine Fault on New Zealand. It has a clay ridge gouge which takes up most of the slip, so shear occurs in here. This is the damage zone, fractured, but full of white stuff, which is mostly calcite, but it's precipitate that fills in the fractures. So in that case, you have a damage zone, but that damage zone seals from the fluids that move through it, and you no longer have necessarily a permeable zone around the fault. So those are a couple of end members of fault zone structure that's been talked about quite a lot through the literature. So there's the original sort of idea of a fault core with a damage zone around it. Chester and Logan, for example, on the Punchbowl Fault. Faulkner and others described the Calaveras Fault in Spain like this, with lots of fault slip zones within a wide damage zone. So one or multiple cores. Why does that matter? It matters a bit mechanically in terms of, okay, do you have one slip zone you keep activating, or do you keep making new ones? It matters for fault zone permeability in the sense that it's a plot of core volume against damage zone volume. That just says, well, if you've just got, say, something like the San Gabriel, you have a local barrier, so a single slip zone, that's the barrier to flow, and it doesn't have much of a damage zone around it. Damage zone is low. If you increase the amount of damage around it, then you basically have a conduit with some barriers. And if you have very little core and lots of damage, like in accretionary prisms, then you basically have a distributed conduit for fluid flow and not much that gets in the way. So, which of these structures you have and the details of it does matter for whether you have a fault zone that can carry fluid or whether you don't, how anisotropic that flow might be, and so on. There's a few scaling relations that I'm just going to touch on. People have thought about fault growth for a long time, and how faults accumulate displacement as they get bigger. But just briefly, so think of a fault like this, similar to the previous diagrams, except we're now looking at a dip slip fault. This is just to recap some terminology. So the fault core is the central bit that takes up most of the sliding, most of the shear strain. Around it is a damage zone. So that's, when we talk about fault zone width, we tend to talk about the whole thing, unless specifying that it's the fault core thickness. I should make the point too that this damage zone often has some chemical alteration because it tends to be a fluid conduit. We've talked about damage zones without really thinking too much about what they look like and what they do and how they're measured. So when you see measurements of damage zone width, there's often a lot that goes into that, but it's basically the width where the fracture intensity is greater than the background. This is out of Manon Carpenter's master's, but basically she has some microstructural images near the fault. So you see quite a lot of brown, that's clays that have replaced feldspar. Fractures are a bit hard to see there, but here they're in red. So lots of fractures near the fault, generally quite short, lots of orientations. Again, clay stands out. So what used to be feldspar is now yellow, altered to clays. Here there's not much shear displacement, so you just have it patchy within the fracture system, doesn't do much to the mechanics, but shows you the alteration part of fluid flow through the damage zone. And fracture orientations are all over the place. We go a bit further from the fault, bit less alteration, bit less fractures. The fractures are a bit more organized. We go outside the damage zone proper, maybe still a little bit elevated fractures, but we now have mostly intact, unaltered rocks. And we go well outside the damage zone, not really any fractures anymore, no clays. The fractures are in a different orientation than near the fault. So these are fault parallel. These are different orientation, unrelated, no longer in damage that's related to the fault. So when we talk about damage zones, they're really where there's lots of fractures. Fractures are often a large range of orientations, and they allow some alteration of the rocks. Damage zones and fault, so various fault zone parameters scale with the size of the fault, similar to how slip in earthquakes might scale. There's been a lot of discussion about fault growth and the displacement length scaling of faults. So this is length against displacement. Don't see the background very well. There's lots of gray dots at the back here that don't show up particularly well, sorry. But basically there is a linear relation in log-log space with a scaling of somewhere between 10 to the minus 3 and 10 to the 0 for displacement against length. So as a fault gets longer, it accumulates more and more displacement. These lines are places where Rotevatn and others have been able to determine how this varies with time. And their argument, so the argument for a long time has been, how does this relationship arise? Does a fault start down here and then just grow and get longer and more displacement? Or does it start somewhere with a set length, and then as it accumulates displacement, it does that until it hits some maximum that the length can handle? Their argument, the current argument seems to be, there's a little bit of both, but faults link up fast, and then most of the history you see is accruing displacement on a fixed length. So you make a large fault quickly, and then it spends a lifetime more or less pinned at the edges. At least not much seems to change. Still some debate, but that seems to be the current story. The damage zone thickness also accumulates in some way with displacement, so bigger faults have bigger damage zones, but only to a point. So there, if we start at fault that has just a little bit of displacement, a few meters, it will have a damage zone width that's a bit less than that. Then it tends to accrue damage as more displacement occurs, but at about 100 meters of displacement as a break-in slope. So we don't have faults with tens, hundreds kilometers of displacement don't keep scaling like this and end up with many kilometers of damage zone. It seems to saturate. And in this collation of data, which is a collation of many other collations, no one's really got anything with more than about a kilometer. So you're only damaging so far from the fault before it stops. In this idea of purely brittle fault, core, and damage zones. That is maybe not the end of the story. So all the faults I've shown you so far are localized cores in fractured host rock, where the fractured host rock does not really accumulate much shear. This classic damage zone concept implies that the damage zone has lots of fracturing, but very little shear strain. But there are many faults. This is an example from the Outer Hebrides. Dates back to Simpson 77, but more work recently by Imber and Holdsworth and others. In this case, you don't really see that core damage zone combination. What you see is lots of very sheared phyllosilicate-rich rocks surrounding some blocks that retain the protolith composition. So these are in granulites, granites, essentially mechanically. And you see blocks of these intact rocks that are not phyllosilicate-rich, surrounded by phyllosilicates. And similar in a subduction zone system in Japan. In this case, what used to be oceanic crust has been altered to chlorite and takes up shear over a broad zone. So instead of a fracture damage zone, we have a highly sheared wide zone. In both these cases, that is developed through fracture alteration and shearing. So again, you might start off with something that's a classic damage zone, lots of fractures, but if you can alter that, and Cristiano Colatini and others have a good review on this concept a few years ago, 2019. If you fracture it and then start making weak minerals, clays, chlorite, serpentine, pick your mineral depending on your protolith. When that starts interlinking, instead of deforming on some localized core somewhere, it's easier for the fault to just distribute shear through a wide zone. And you end up with something quite different from that original damage zone fault core setup. To just show a specific example of how that can happen, that is Sophie Cox's PhD. A really classic site for this is oceanic transforms, where you have no lack of fluids, no lack of deformation. You're starting with dolerite dikes, so you already got a set of vertical fractures to slip along and to put fluids along. So as you deform that a bit more, there's the intact example. You deform it, you start having shear, so steep strike slip faults along the existing dolerites. You start making fine-grained gouges, and you start having fluids come through it. You get more and more of that. You don't really recognize the dolerite dikes anymore. And you end up with this, which is hundreds of kilometers of a really fine, very phyllosilicate-rich, depending on depth, it's chlorite or serpentine, shear zone. And mechanically, taking that same example, so if we took those samples to Matikari in Bremen and sort of said, well, if we shear the dolerite, then you've got something that's velocity weakening and strong, somewhere between 0.6 and 0.8 friction, A minus B well under zero. As you start adding a little bit of clays to it, not very much happens because it's not interlinked. But then you start adding more, so the amount of dolerite is down to about 40%, clay is about 60%. Then it becomes stable, becomes much weaker, and when it's basically just clays with a bit of dolerite chunks, it's very stable, very weak. So it's a way of, just simply by developing fault zone structure, you go from something that is strong, velocity weakening, you alter it, break it apart, and make it into something that is much weaker and stable. And just to show what that looks like, in the weakening, in the strong velocity weakening dolerite, you basically get nice localized slip surfaces. As you start adding clays, that starts to get wider, starts to generate a foliation. When you're basically just shearing gouge, much more developed foliation with some localized slip surfaces, Rheedal shears, foliation, so on. Not too different from the Montmorillonite that we looked at yesterday. Another end member, now in that case, we have a phyllosilicate-rich fault zone because we made it. We started with something that wasn't, we deformed it, altered it, made a wide fault zone. The other example is if you have something that has a lot of phyllosilicates in it already. So you take a subduction zone, you have an incoming sequence of muddy and sandy sediments, you shear it, and you get something like this. I've rotated this back from outcrop to original orientation. So low angle thrust, interconnected mudstones, clay-rich rocks with chunks of sandstone that's there because you've dragged the sandstone layers along. Rowe and others reviewed this and basically say, what we tend to see in subduction zones and lots of melanges around the world. And Andreas showed that you could say something similar in seismic data as well, is that you've got hundreds of meters of this sort of melange with what used to be sedimentary layering pulled along. It might also well incorporate bits of oceanic crust. Altered and unaltered crust gives you similarly chunks of strong and weak. But one point is not all of that is active at once. Now, we don't have control on time here, but we kind of know from the structures that we're dealing with packages that are tens to hundreds of meters wide that are active at any one time within this much wider mess. But again, this isn't a punch bowl type localized fault core in a damage zone. It's something that's much more of a wide shear zone with planes, occasional shear planes within it. So to try and summarize that, what we're seeing in geology is really faults are highly variable. Some are planes with not much around them. Some are planes with a damage zone that may or may not be sealed. Some are host rock altered into a wide, weak shear zone, and some start off with a range of materials from their protolith. Okay, to just stop myself and summarize a little bit. Why does this matter? There's an importance for a mechanical point of view in that some faults might have bialy friction for good reason, depending on where it is, how it developed. Some other faults might be mechanically weak, again for good reason, how they developed. That can vary along strike, can vary between faults. And there's a hydraulic importance because depending on the fault zone structure, it might be permeable, it might not be. It might be time dependent, it might not be. I haven't talked about this whole other story. There's also some effective fault healing. Some of the fault structures will be much more conducive to heal fast versus others. So to try and summarize that, we kind of, we got the two examples from Faulkner et al. Of we have a local zone and a damage zone. You can imagine that happens if, think about the fault strength versus the wall rock strength. If the fault strength is really low relative to the wall rock, there is no reason for the fault to move out of its nice single plane. It's just going to stay there. If the fault is relatively strong, still got to be weaker than the wall rock, otherwise you just make more. But if the strengths are comparable, then, and the fault core heals easily, then you make a fault core, but then there's no reason to use it again because it's easier to make a new one. And you end up with this sort of thing. That's if you localize your slip in the fault cores and the damage zone is sort of passive in terms of shear. If you start shearing the wall rock, then if the fault and the wall rock are relatively similar strengths, you get something like this, so a broad zone of stuff that forms in similar ways, and if they are quite different, then you might end up with localized shear along where you've made a weak rock and hard blocks elsewhere. So that was sort of an attempt at making some sense of the different variations in faults and why they happen. Now within all of these there's an inherent heterogeneity, which is a term we throw around a lot without necessarily knowing what it means, because sometimes we don't have the data to know. It also depends on scale. So you can talk about heterogeneity at a fault plane scale and in the lab, where what you have is asperities, contact points of real contact, and you have areas that either filled with a weak gouge or with air, and you have some real area of contact, and that heterogeneity controls small scale friction. You can scale that up to the outcrop, and think about, okay, we have many planes like this in red that have their own inherent small-scale heterogeneity, but they will interact, and they might be embedded in something that is weak with some stronger bits, and then that implies another heterogeneity, and then you have the fluid flow through that. So there's an outcrop scale heterogeneity that might matter at that scale. And then we have this diagram that's been shown a few times where you have asperities, whatever that means. It's not the same as that. It's something that is, for some reason, behaving, say, in a way where it releases more moment, or where it's just locked while the material around it creeps. And you might have some asperities that create low-frequency earthquakes within slow slip events. They may or may not be the same kind of asperity as that, so different colors. So there's variable heterogeneity where we know quite well what it is and where we don't really know what it is. At least I don't think I know what it is. So let's think a little bit about what this could be. Thinking back to, okay, we've thought about what fault zone structure might be. We've thought about what materials, properties we might have. So what matters? Well, one thing we've thought of that's been around for a long time is, well, fault orientation matters because it will affect the stress on the fault. So here's an example from New Zealand. Ake Fagereng, here's a slow slip event in red. Here is the fault, so I'm going to just use a geophysical example for this one. So here is, we had an array out for NZ3D. This was 49 broadband seismometers in a 20 by 10 kilometer array. Andreas has said why receiver functions are problematic, but we'll show some anyway. What we know about this is we've kind of inferred over time that there is a seamount, some seamounts in here near the trench. And there's been a question, okay, what happens at the edge of this slow slip event? So greatest slip in red. So this array sits over where it doesn't slip very much, basically the end of the slow slip event. If we map out the interface and receiver functions, okay, this is coarse, but you do see a variety in orientation. It kind of goes quite flat and then steps and steps again. See it a bit more highlighted there. We infer this to just be a continuity of we know this subduction zone is very rough going into the subduction zone. We take this as, this was Harry Lee's PhD. He took this as, okay, that roughness is maintained. And what I'm really getting at here is, well, we've got this map of fault orientation. This just has in colors the height of the interface relative to a planar surface. So it's not planar. It varies by about plus minus 2 kilometers. Again, the resolution here isn't great, but it's better than 4 kilometers. So we know that, okay, here the interface is relatively high compared to a planar surface. Then it goes deeper. If you change that into shear stress, what basically happens is we've got a low shear stress because the plane is well oriented for failure, and then the shear stress increases pretty much where the slip spell changes. So it seems like there's some increase, there's a geometrical barrier that in this example might stop the slow slip just by increasing the stress. And you see similar things in many places. It's not far from the only place where geometry creates barriers or changes the slip styles. Composition and texture might matter. Mayor Thomas' work on Taiwan with Jean-Philippe, they basically pointed out here that, just showing creep rates, that along here where it's red and green, there is a lot of creep, basically enough to take up the tectonic strain. If you compare that to a geological map, where that creep is where the lychee melange is. So a rock unit that is like the melange I showed earlier, fine-grained, phyllosilicate rich, shears easily by pressure solution. So geologically, this has set up the creep while the rest of the rocks seem to be locked. So composition can matter, texture can matter. You can make heterogeneity dressed with texture as well by just having the same rock, but textures vary. Back to Sophie Cox's PhD on transforms. This is serpentine. Everything in here is lizardite, except for a little bit of chrysotile along some faults. But it's basically one serpentine. Darker green is essentially underformed. The light green is more highly sheared. The red is local slip surfaces. And if you look at the edges of something strong or something low strain versus something high strain, the high strain zone's basically just where the serpentine is well oriented and you can slide along it. And you go away from that, still serpentine, but much more messy texture, difficult to slide. You see the same thing in some mantle wedge shear zones back to Nagasaki in Japan. This is at the microscale. You have well-oriented foliated serpentine that is taking up the deformation around lenses. So again, you have a sort of matrix and strong lenses, but here they are exactly the same composition. The shear zones are antigorite, the blocks are antigorite, but here you can see the crystals are every which way, which is how it forms initially when you just serpentinize olivine. But then here it's got itself oriented and it's much weaker. We also see that in experiments. This is from Andre Niemeyer's lab. We took some antigorite, or Andre's students took some antigorite, they sheared it at 500 degrees. It was really strong. It was about friction of 0.6, 0.7. It was stick slipping, and it created a cataclastic mess in its microstructure. Same stuff, same temperature. We added a little bit of quartz to it. What the quartz does is increase the solubility of antigorite, and friction drops to 0.2, and it becomes stable, stops stick slipping, and you get nice fabric in the serpentine. And the solubility means that it doesn't create asperities, it just stays nice and flat. So same stuff, very small change in composition, which doesn't really help mechanically. The quartz is just sitting in little chunks here and there, but it changes the style of deformation. It's basically a way of forcing the serpentine to deform by pressure solution creep. In nature, this is basically doing the same as that. Here there's not really any quartz around, but the formation is slower. We just can't replicate that in the lab. So the trick of increasing solubility is basically a way of getting the slow enough strain rates in the lab to create the structures we see in nature. Fluid pressure, obviously that keeps coming up as well as a way of creating heterogeneity. It can change slip style. The typical argument for why you have tremor at depth in subduction zones, here from Shelley et al. In Japan. So you have a locked interface where it's relatively dry, VP Vs is low, and then where you have high fluid pressure, you change the behavior to the volumetric tremor. Similarly, there are inferences from many subduction zones about fluid pressure controlling coupling. This is from Alaska, but you could show something very similar from Hikurangi. The locked section has here fortunately the velocity, the VP color scheme is opposite to here. So the blue is relatively high velocities, and then you have a low velocity layer, a continuous thick low velocity layer along the interface. In places that are locked, places that are creeping, it is messier. There is some low velocity, but it's thin, it's a bit patchy, and that seems to correlate with more creeping segments for some reason. You could also have just a general change in the formation mechanism. Red River Fault in China, locked patch, creeping patch. In the locked patch, rocks that have come up from the mid-crust are basically myelonites with some pseudotechylites here and there. And from the creeping section, they are cataclastic, they are wetter. And the difference we see is basically from, I'll do this quickly, pseudotaculite forming dry rocks in one place, rocks dominated by pressure solution in the other. So high stress rocks in the locked region and lowest stress, different deformation mechanisms dominating in the creeping region. Those are all examples from greater depth. Just very briefly, if we go to places where we have drilled into, or someone's drilled into, subduction thrusts at shallow depth, where we know that there's a big variation between slow slip, tsunami earthquakes, repeaters, everything else. Here in Hikurangi, drilling through the Papaku fault, what we see there is a mixture of breccias that look like that. What looks like essentially mylonites, except these are really shallow clay-rich rocks, and some mixtures of those two things. If we look at it schematically, the fault zone there it has a damage zone above it, and then it's got about 60 meters of this kind of thing, breccias, shear zones, breccias, shear zones, down into a relatively undeformed footwall. The point here is there is no discernible compositional variation in any of this. This is all just a fairly homogeneous silt. So there is something else in this case that makes this deformation style swap between localized and distributed. Nankai Treff, same thing. Wide shear zones with little faults in them. If we look at it in detail, you have well-developed fabric, but then that is cut through by local faults. Not much compositional variation, nothing really seems to govern where these are, but at this very low effective stress, small variations that are not compositional is sort of throwing us between distributed and localized. So, effects of faults on heterogeneity. Point is, regardless of the reason, and there's lots of reasons you can have it, there's going to be spatial variations in response to the remote stress. Could be fluids, could be composition. And that means some faults are going to be aseismic, some faults are going to be building up elastic strain in the rock around them. And another point is that is then self-generating and more of a stress heterogeneity, because something is slipping and something else isn't, then you have a gradient that creates more heterogeneity again. Okay, let's try and just think a bit more about how do we deal with this? Or can we say something, do we have any rules about what actually happens, or what controls what? Lots of heterogeneity, maybe some of it matters, maybe some of it doesn't. If you think of all of this in terms of a polyphase fault zone, it could be at any scale really. What you have is some material deforms easily, some doesn't. Here, the case of a melange, strong blocks, weak matrix. What you really get is a variety of strain rate. You get some areas that deform relatively fast, some are stationary. And the question is really whether that faster deformation is enough to accumulate all the strain or all the remote stress, or whether you need to occasionally deform the whole thing in some other way. And that really comes down to a competition between deformation mechanisms. So this is an example from Handy, Mark Handy's group back in the 90s. They had a few examples of how to deal with this with polyphase rocks. And there's a couple of points to point out here. So what they've done is plot strength against amount of weak material. One is basically the strength relative to the strongest material. So here it's the strongest material. Here it's much weaker. And if you've got very little weak material, you basically have this, the sort of interconnected framework of the strong stuff. You have little patches of clay in red, but otherwise it's a breccia. It behaves like a cataclysite, behaves frictionally. As you add a bit of the weaker material, if the difference in strength is not very big, then it's going to behave as some kind of average. And you get something like this if it's ductile, or you get lots of slip zones in the damage zone if it's frictional. But you then behave roughly as an average. But if it's a lot weaker, you're basically just going to drop to the strength of the weak stuff. So viscosity ratio matters. If the viscosity ratio is small, then the heterogeneity doesn't really play that big a role. You just get something that behaves like an average. If the strong material really dominates, or the weak material really dominates, then that would be the rheology that is mainly in control. But that might change with time. What we see if we go to polyphase faults is some places you have, even if you have a much stronger block, that is fractured, so it must occasionally deform. And you have basically three things going on. You have the blocks deforming in a way, you have the matrix deforming in another way, and then you might have some localized slip surfaces that deform in a third way. And it's, how do you switch over time between those different mechanisms? That kind of the same thing. So let's think briefly about really weak faults. So think about the wide shear zone of phyllosilicate, probably deforming by some sort of combination of pressure solution and frictional sliding if we're in the seismogenic zone. So in this case, you have some stuff that dissolves and then weak clay-rich surfaces that take up the sliding. The dissolution means it doesn't create too many sticking points. And if we plot that, the strength of that, you have an interplay between frictional sliding along phyllosilicate surfaces. Quartz is probably relatively passive because it's the strongest thing around. And then if you have a wide shear zone, so strain rate is low, then it's quite easy to deform by pressure solution. So at some depth, if strain rate is constant, that takes over and you get a relatively shallow transition from frictional sliding to dominantly ductile. If it's narrower, that goes deeper. If you change the strain rate, you move back and forth. So deforming thickness then becomes a control. But if we look at that in detail, this is an example from the Schumanto complex. What we have is, there's a bulk that deforms by pressure solution, but inside that we tend to get vein swarms that show some evidence that occasionally you still get localized slip deformed frictionally along. And the thing is, pressure solution basically makes clay-rich surfaces that are going to be weak. So it somewhat supports that occasionally you will have frictional sliding along those surfaces. So what kind of slip do you get? If we zoom in on those surfaces, they tend to be, they're coated in quartz, or we zoom in on the vein, sorry. What you see is you get vein-coated surfaces. They are parallel to the stylolites, or to the pressure solution surfaces. They're linked by tensile veins at a high angle. So if they mimic or they track sigma 1, so you have a very high angle between the compressive stress and the slip surfaces, because the slip surfaces form essentially perpendicular to sigma 1. So in a sort of more circle view, to reactivate this foliation, even if it's very weak, it's at a bad angle, so you basically need the fluid pressure to increase locally. So the way you get, theoretically, you might just get pressure solution creep along these big phyllosilicate shear zones without any frictional reactivation, but you do have the weak surfaces. So if fluid pressure is locally high, then those might well activate. But one point that Chris is making, if you do that, you basically by definition put this effective stress to 0, which is going to push your K sub C towards 0. So it's going to be quite hard to create an instability on these things. But they're not stable. Because if you look at them in detail, they're built up of lots of little increments of sliding, like a few microns each. This is in Crystal Beach in New Zealand. This is in Schumanto in the Makimina melange in Japan. Same kind of thing. Same kind of step sizes. So the way these like slip surfaces within a frictional viscous flow seem to work is that you activate one, but it's really hard to make it slip, so it steps to another one, steps to another one, steps to another one. And you end up, after doing that many times, you get this sort of structure. If you play some games with that, so you measure the size of those increments. That's done in the Otago schist in New Zealand and Japan. The sizes are about the same. They're on sort of tens of microns along slip surfaces that are meters to tens of meters. You play some games with the slip length ratio and assume some shear modulus, and you get stress drops of kilopascals to hundreds of kilopascals, but tiny. So in this setting, if you create an instability, it's difficult to sustain. Stress drops are very small. I'll skip that. And there's these kind of structures reported in a few places. We compared it to, is this tremor? I mean, maybe it is. You see tremor everywhere that's in various colors here. These examples come from these spots. So maybe it's one kind of evidence for tremor. It's at least the right kind of stress drop, right kind of structure. I'm not saying it's the only one, because there must be many other ways of doing it. Otherwise, you wouldn't have it everywhere. The other point, putting this on this PT diagram, is all the three locations where these kind of structures are well documented lie on dehydration reactions. So they are related to where you can get a lot of fluids locally. This is on blue schist, lawsonite out. The Japanese example is pumpelliite out. The New Zealand example is dehydration of micas. But it is an example of fluid-driven change in mechanism. You have something that's happily creeping along through easy pressure solution creep. But if you can build up the fluid pressure inside that, frictional sliding becomes so easy that it flicks. But it doesn't do it for very long, because it becomes stable and locks itself up, and then precipitates something in there so it hardens again, and then you have a cycle. Ooh, okay. That's all right. One more example, and this one's quick. Okay, totally different setting. Lower crust, Lofoten, in an orthosite, so feldspar-rich rock. You see a white line going off into the distance for hundreds of meters. It's white because it's full of fractures around the pseudotaculite that just cuts straight through all the fabric. So you've got lower crustal rock, very dry, occasionally fails in earthquakes. Lucy Campbell's model for how that happens, so you have a few shear zones. They look like that. They're either reactivating dikes or reactivating pseudotaculites or some other heterogeneity that is typically fine-grained and a little bit wet. But if you're deforming along those, again, you end up with this sort of mixture of shear and something very hard. And a model is something like this. You're shearing on a number of shear zones, but you've got something hard between them. You have a strain rate gradient. This is going to fail at some point. It can't creep, so you get a small local earthquake. Basically, in a Christmas diagram, Christmas tree diagram, you have some strong frictional rock. If you have a weak shear zone, great, that'll work. But if you can't do everything, then deforming the intact rock or coarser grained rock with dislocation creep is so difficult that you instead create local earthquakes. These are a very different feature. Again, we played some games with fault length and displacement. They have centimeters of displacement on just a few meters of fault length. So they plot, compared to, say, Wilson Coppersmith, they have very high displacement for their length. You turn that into a stress drop, they end up here. So stress drop of hundreds of megapascal to gigapascals. It does fit roughly right if you have a complete stress drop. So if you basically go from, you have stresses of hundreds of megapascal to gigapascal at this sort of depth, you then fail it, put a weak pseudotachylite there, stress drops essentially to zero over the fault plane, and you have very different stress drop from what we had in, say, triggering frictional sliding by fluid pressure in a otherwise weak fault zone. So what I've tried to show in a few different places, a few different ways, is fault zones have weak and strong components. And those strong components, even if they're passive, they do have some effect because they create strain rate gradients, they might fail. If you look at it in detail, if you look at where the faults form, they don't form in the strong stuff, they form at the edges. So if you look at slip surfaces within a melange, they generally sort of hug the edges of clasts and then step between them. So they're really driven by rather the strain rate gradient than by, say, a clast being stronger and then failing. Although there's a bit of that too. Nice old paper, or oldish, Kenkman and Dresen sort of highlighted this in that, okay, you have a strong thing within something weaker. What you see if you plot the grain size is that this fine grain size reflecting higher stresses is what you see at the corners. So this with sinister shear, here you get some higher stresses, here you get some higher stresses. And the stress increase near that block is on the order of a few times the average stress, depending on how well coupled it is. If you can just spin, then it doesn't elevate the stress. But if it's coupled, then it does that. So I'm not going to go into these models in any detail. These are some more recent linear viscous models that Adam Beal did. But the point is the same. Plotting strain rate, we've got in dark blue, there are some stronger blocks. They're surrounded by a matrix. The high strain rate in yellow happens at the edges of those, where you're stuck with a little bit of weak material that has to deform. You locally make the strain rate high. If you locally make the strain rate high, you might no longer be able to deform viscously, and you switch the mechanism. So, final way of a way to think about this, or to think about stresses and faults. If you take that same as on the previous picture, if you make the stress close to the frictional yield, it doesn't have to be at it because stresses are elevated around the stronger blocks. So if the average stress is about, or the driving stress is about 80-90% of yield, the whole thing yields. Because locally, the stress is going to be higher because you elevate it in the strong stuff. And then as you decrease the stress, for example, because viscous creep is more efficient, is relatively efficient, so it doesn't build up high stresses, then you get something that's a bit more mixed. You have a matrix that deforms viscously, and then in some areas, you start failing the clasts again, because even though the stress is quite a long way from the yield, locally, it's hitting the yield because you elevate the stresses in your asperities. And this could be any scale. This could be a shear zone over kilometers, or it could be a local gouge. And then if you can keep things going at a very low stress, you're stopping to see the yielding because you're no longer elevating the stress enough. So really, one way of simplifying all this heterogeneity is say, well, if the heterogeneity is such that everything is just going to be frictional because the stress is high, then that's what happens. And it doesn't matter what matrix is. You have one behavior. And similarly, if you can keep the stress very low, like the matrix is very weak, then the competent class is somewhat passengers. And then you have this intermediate thing where things just are going to be more complicated. And the numbers here are not important, they're case specific, but you basically think of it like this, that you have a viscosity ratio and you have a stress ratio. And if you've got no heterogeneity whatsoever, then it's either viscous, because that's what it prefers, or it flicks to frictional, just in a sort of first order broad behavior. If it's really variable, then you have, you don't need to increase the stress, so this is driving stress versus yield, very much before you start seeing some frictional deformation, because the difference in strength is very big, so in your local strongest spots are going to change behavior quite easily. So how much heterogeneity you have, or how heterogeneous the system is, controls just how much variability in behavior you can have, but you don't need much heterogeneity to have variability. So you can have models where there's no heterogeneity and you still get a range of behaviors, but it's easier to get the range of behaviors if you have more heterogeneity. So I'm going to skip those specific things, and which were kind of there if I had extra time, and leave with a few points. Basically, what I tried to do was sort of review a bit of what is the variation we see in fault zones. And generally what we see is a mix of behaviors over some zone. It can be principal slip zones in a damaged zone of little shear strain. It can be principal slip zones in a wide zone of lots of shear strain. Depends on what you're deforming and what its history is. Lots of options. Which means fault zones are heterogeneous for lots of reasons. And in those fault zones, you get a range of structures, and those structures are useful because they tell us something about what sort of behavior we've seen, what sort of behavior you can get in particular situations. And the end point, the point I really tried to make is the fault zone rheology depends on competition between how it deforms. And because of that, that's time dependent, you can get lots of different behaviors in the same fault as it develops over time. And I'll stop there.
Any questions from postdocs, students, or the scientists? Yeah.
One question, like in the scaling law that you showed at the beginning, where the damage zone was saturated in a point, is there the possibility that this is an observational bias? So in the fact that after a while, there's no geologist that can go there and say, and keep looking at 10 kilometers of places.
So I think I think most faults this is measurable, because all you need to know is whether the wall rock fracture intensity is greater than the background. So if you go further and further from the fault, at some point you just stop seeing that increased fracture intensity. And there's places where this is measured quite great detail and quite easily. So, I mean, it's difficult to define exactly what the background is and exactly when you've hit that and so on, but you do have places where it's quite easy to do that, because you don't need continuous outcrop, anything like that. You just need enough. Okay, it depends on lithology, and there's certainly biases, but I think if there were places where the damage zone was much bigger than that, we would know.
Any questions from students, postdoc? I want to wait a bit. Any questions? Oh, okay. Should we move? Okay. You have.
So, okay, great talk. I mean, I'm always amazed to see what is the range behavior of the geological fault zones. The structures. We'll be lucky if we can capture 1%, from seismic imaging, simulations. We are putting damage, but I know it's an oversimplified simulation already. But I just wonder, if you think about the generation of large earthquakes, just don't talk about slow earthquakes or tremors, those kind of things. What will be the most relevant first order things that we need to capture here? So it's like the simulations we are doing, all these fault deformation. Can we just say all these map shear zones, secondary fractures, deformations are captured by the fault deformation in these kind of simulations or not? How bad is our assumption that we have a principal surface and damage zone?
I think for some faults that's a very good assumption, and for some faults it definitely isn't. So
Like the large earthquake faults.
So it seems like we can get large earthquakes in faults in subduction zones. Right? We know we can get magnitude 9s in subduction zones. They definitely don't look like that. They are not principal slip zones in a damage zone. They are broad shear zones that might well have principal zones, slip zones within them. And I think there the question is how efficient are those faults at the forming without an earthquake? And if they are very efficient at that, you just don't build up the stress. If they are not efficient, then at some point you're going to need the earthquake because you're building up the strain. So in those, I think it's really the balance between aseismic deformation and how much slip you need, and can it do it or can't it? And then the size comes down to, I think Adam Beal did some models on this, and lots of people have thought about this. Eric Dunham has thought about this too. A lot comes down to then the stress heterogeneity, because if it's roughly the same everywhere, you'll get to near failure just about everywhere, and then you can get a big earthquake. If you just have small patches where you're accumulating strain and everything in between, you're getting rid of the stress by other mechanisms, then you just can't bridge those spots where you have the stress to create a big earthquake, and you're going to get lots of small ones. So, I think the simulation, we know that because of the simulations. So I think that's what, it's the stress distribution, or stress versus strength distributions, and then making the assumptions that are relevant to the fault you're thinking about, which might be very different depending on your setting. Does that make sense?
We can talk about it.
Yeah, hi. Very nice talk, very inspiring. So all of us, I think, want to build more and more realistic representation of earthquake generation, and then push this towards seismic hazard mitigation. And you showed us, what you see in the field, and even some models that can reproduce mustering. So how do we go about taking it to the next step? And what do you think the constitutive behavior of these melanges are? And how can we take this to the numerics and upscale it to much larger scales? I'll give you $1 million, 5 years.
Yeah. I have roughly that. Yeah, I mean, that is the $1 million question, right? How do we go from this complexity at the outcrop scale to what matters at the larger scale? I think, again, it's this balance between the different ways that a fault can accumulate strain and what controls that. And then the tricky thing is having specific examples where we know well enough what's down there to say, okay, can we test this against reality? Can we reproduce what we see in a real fault based on what we think the compositions are, the fluid pressures are? What is the what do we think are the controlling factors at depth? And that's kind of what I tried to do with the slides at the end. Is okay, can we at least think of some way of parameterizing it? Do we have a good enough understanding of what the stresses are, or what the stress distribution is, and how it varies over time? But it's tricky, and I think coming up with some way of parameterizing what we see at the small scale, figuring out exactly which parameters is it that matters, because we can't model everything. So simple simulations, where we what's the minimum number of variables we can use to describe what happens in reality? Observations on time dependency, like the stuff Roland was showing yesterday. What kind of asperities are we actually dealing with in the real world? Are these locked zones really big locked areas, or are they actually just little spots? That's kind of easier to explain. And then it's how they communicate. And do we know something about the material that communicates? How did that develop with time? So time-dependent observations as much as possible. Any kind of second independent measure of what the fluids are doing. How much is fluids, how much is stress transfer? Can we constrain that? And then what comes from the geology is what's possible. What are the possible constraints and which ones matter and which ones don't in a particular spot. If you know there's no fluids, then don't worry about it. Model with something else. If you know it's full of fluids, then worry about it and think about, well, where's the permeability in this situation. So I think a combination of the geological observations that we can't make directly in actively deforming places, but we can make them elsewhere and say, well, these are the possibilities. If it isn't within that realm of possibilities, don't worry about it. And the geophysics from a particular places, the more we know, and the more we know about the time dependency, the better. But we can talk about this for days.
So at some point you showed some PT diagrams, and you mentioned that the areas that are creeping are probably self-fed by local fluids because they are sitting at the place of metamorphic reactions. So I think it's quite interesting. So is this really true? And and after that, where do the fluid go? And do you see any evidence of what is the migration of fluid and where they could act, like to help the matrix to?
Okay, so 2 parts. I think metamorphism is really important, and we keep forgetting about it. But the point I was trying to make there was where you have lots of local fluids is where you can most easily change your behavior from creep to something else for a little while. Because you can build up the local fluid pressure, and then if you can't go anywhere, then it will get high enough and you're going to get frictional failure within something that is nominally creeping. At that point, you create permeability and the fluid moves away wherever the permeability is. And there's a competition there between fluid flow and deformation. Again, that's been explored by quite a few people, but again, it's something to keep in mind. And I didn't really talk very much about it, but if you look at a creeping fault zone, it tends to be foliated. Fluid flow permeability tends to be very anisotropic. But if it's moving and has that foliation, then you have a mechanism of moving fluid along that fault. Very difficult to move it out unless you fracture it. And that's probably how you can have large creeping areas, because you then get your fluid from the source and up through the creeping fault system. And then, if it's flowing, then it's not creating overpressure, so it's not creating frictional sliding, or local frictional failure, and you can get a big creeping zone where you can keep the fluids flowing. And then if you have a barrier, then you might have a problem keeping that going, or change the mechanism. But the places where you have lots of local fluid release seems to be, and this seems to fit with at least some swarm activity and some tremor activity, that it's where you have a local metamorphic reaction. Not necessarily one magic reaction, probably a whole lot of different ones, depending on the PT space and the PT path and the composition.
There's someone after Brittany, I think. I think there's someone.
Yeah, go ahead. So, two more. You and Chris and Jeff Eaton. That's it. Yeah.
Thank you. Great talk. Very inspiring. There are some theoretical evidence that when you activate multiphysics couplings for fluid diffusion and temperature, you have this strain localization zone to travel up and down. And this confirmed also by some numerical simulations. And I was wondering if there is evidence of this gamma dot that you saw to travel during shear deformation.
Very difficult to constrain. I think is the quick answer to that, because we don't really have constraint on time. So you know that there are areas that are interconnected, or the fabrics connect, and it probably varies, or probably then deforming at the same time. Geologically, whether that's the same time or whether that is a pulse that moves, I don't know, and I don't really have a way of measuring that I can think of.
Okay, thank you.
Okay, really nice talk. Thanks very much. I've got a question about heterogeneity. You showed a lot of examples of interesting types of heterogeneity. When I look at that, I often think to myself, how do you decide what the scale is that's important that I could compare to the critical nucleation zone length? Because I think, if I get the heterogeneity,
it somehow influences the nucleation zone length, potential nucleation zone length, and that's the critical scale. You thought about how to characterize that, or say the ratio of some heterogeneity measured to the critical ratio for nucleation?
Only in the sense that you can take the equations that come from the lab and come from rate and state about what the critical nucleation size might be, given some sensible set of parameters that we can estimate. And then, I think in terms of the size of these veins that clearly are local instabilities, we can measure that. And that must have been at least able to nucleate to some extent, so maybe that gives us at least some idea. Maybe where you see these slip surfaces that skip between blocks of different compositions. If what you need, Phillips did some work on this, saying, okay, if we assume a nucleation length that is that comparable to the block sizes that then localize strain rate in that one region, where you can then start something that then jumps to another. So I think we can think about that sort of scaling and how you jump between different areas that might be velocity weakening through a velocity strengthening area. How big a segment can you jump? How big does the nucleation area need to be? But it's a tricky.
While taking Joaquim's question, can the next speaker go on there?
Yes. I have a question regarding the exhumed minerals from subduction zone. When we look at the structures you described, we would think that most of the deformation will be actually a seismic. Right. So you see about a pressure solution creep.
Yeah.
Occasionally it's not applied, but it doesn't. So my question is, do you ever see evidence in such systems for large impedance, for these methods of displacement, something that could be typical of large megathrust layers? Or is it that they don't occur where you have this kind of vacuum fault zone?
So the sort of cop-out answer on that, but I think it's probably true, is they would be really difficult to preserve. So I think if you did have something travel through a pressure solution dominated melange, it would go along, it would localize along one of the very many low friction, high polysilicate surfaces. It would travel through that. It would make some damage along the way. It would be very similar probably to the vein systems we do see, but that are relatively small displacement. And then you would have cycles of pressure solution that would just overprint any evidence you had for that. Is the boring answer, but I think it's probably in many cases true. You do have the occasional pseudotactylite that implies, okay, maybe it sometimes hits something stronger where it melts a bit, and you can see some evidence for it. Few places you see that. Kodiak, Alaska, they seem to have more evidence than elsewhere about. I think that would tend to localize near the top of the melange or near the top of the oceanic crust, and where you have that sort of interfaces, you do see some, especially Kodiak, have reported what looks like bigger displacement surfaces. But I think they would be really hard to preserve. Makes it tricky.
Well, let's thank Ake for the great talk. Alright, so let's move on to the next presentation, which will be given by Joaquim Julve. Please go ahead.
Yeah, thank you. Can you listen to me? Yeah? Okay. So, today basically I'm going to talk about some key results of my PhD. And we were trying to understand basically the geological and the overplay control on the seismic cycle of Chilean megathrust earthquakes. So thank you, Ake, for your talk, because it will be really helpful to try to explain some of the key things that we did here. Because in this work, basically we try to average all the complexity that Ake showed us before into points, and those points will have some properties. So everything will be super simplified, just to keep you that in mind. Okay, so I want to start to showing you right away the Chilean subduction zone. So Chile is a very elongated country, as you see right here. And this thing is very important because it allows some very key differences in the tectonic setting. So in the northern part, you have that the subducted oceanic plate is basically very old. So it has 50 million years. While you move to the southern part, you get that the oceanic subducted plate is younger. It has roughly in between 10 to 0 million years. Another thing that is striking is that you may see here in this plot that the sediment thickness that is infilling the trench increased dramatically from north to south. And the maximum crustal thickness also changes dramatically, because here we have the Altiplano Puna Plateau, which is very thick. And then we reach some average values of the crustal thickness. So please keep this in mind, because it will be very important in order to constrain how is the behavior of the plate interface, the frictional behavior of the plate interface, that will eventually control the seismic behavior. So to try to evaluate all these key parameters, we selected two important cross sections, one in the northern part and one in the southern part. So as you may see also here, the Chilean subduction zone has hosted very important subduction zone earthquakes. And the most important one is the Valdivia earthquake right here, which is the biggest earthquake recorded by modern seismology. It's a 9.5 in 1960. An interesting thing is that 56 years later, it was reawakened by the Chilean earthquake right here. And other important thing is that you see that here we have contour plots of the coseismic slip of some earthquakes that are light blue and some others dark blue. The light blue ones represent earthquakes that are interpreted as rupturing the down deep portion of the megathrust. So you have along the whole margin down deep subduction located earthquakes and very big ones that are able to rupture the entire seismogenic zone up to the trench. So the idea basically is to try to simplify with numerical models the behavior of the blade interface, which is very complex, as Ake showed us, and try to answer this key question, that is how fluids, the geology, meaning the composition of the rocks that are interacting, and the upper blade structure are related to influence the seismic cycle at subduction zones, particularly using the case of Chile. So, yeah, we built two very representative cross-sections, one in the northern one and the other one in the south, as I showed you before. And the first thing that you may see here is that in the northern part we have a lot of data. And in the southern Chile, not that much. Even though we have the biggest earthquake there, we don't have that much data to constrain the foray structure. Still, we were able to do something. So the idea here is that we compiled a lot of seismic wave profiles, temperature models, background seismicity, locking degree models, co-seismic slip models, the structural geology to define the upper plate structure, tomographies, and so on. And all this is simplified in this cross-section just to define different frictional segments. So we have velocity strengthening segments right before the outer wedge, velocity weakening domain representing the seismogenic zone, and velocity strengthening domain below the continental Mojo, where strikingly, if you remember the crustal thickness, you see that the Mojo intersection ends up right here, just where seismicity ends, which is the same feature that you can see in northern Chile right here. So it has been interpreted that interplate seismicity ends roughly at this depth, where you have this isotherm, while in this case, the 350 isotherm is way, way down deep, but still the seismicity ends up here. So the question is, well, what is the role of this upper plate structure regarding the nucleation of earthquakes? And here you just have a new cross-section just to show you that if you remember the variation in sediment thickness in the trench infill, you see that this generates a subduction channel that is very well observed in southern Chile, which is roughly 1 kilometer thick. And in the northern part, you just have the plate interface interacting with the upper plate in a configuration where you have hosts and grabens because of the bending of the plate. So we try to model this using numerical simulations, using the code Unicycle, which is a code developed by Sylvain. And we use this rate and state friction law, but the key thing here is that with these observations and with these geological assumptions, we can say something about A, B, and friction coefficient. So if we have sediments here, and we know the composition roughly of these sediments, we can say, okay, we assume that in this seismogenic zone, the frictional parameters will be controlled by, in this case, granites and quartz that came from the erosion from the main cordillera, the Andean Cordillera. While here, we don't have anything. So we have basically the subducted plate just interacting with the upper plate, and we assume that altered basalts from the oceanic plate are controlling the frictional behavior in the seismogenic zone. Okay. So now I'm going to show you the first results for southern Chile. And here the main idea was to try to observe one concept proposed by Marcos Moreno in 2018. He studied the Chilean earthquake quite deeply, and he found that the lower part is accumulating more traction over time and thus generating earthquakes located down deep more frequently in time. And this has a mechanical relationship with the occurrence of very large earthquakes as the Valdivia one that ruptured the entire seismogenic zone up to the trench. So basically, here I'm going to show you just preferred models because I don't have time to show you everything. But what we did was to, using the same assumptions that I showed you before for southern Chile, we ran a simulation trying to mimic this idea. So since effective normal stress depends on the pore pressure ratio, we can change it along deep and see what happens. And we get that we have a seismic cycle represented in this figure where red colors are high slip rate and blue colors are low slip rate. So these lines right here are basically one earthquake, and you can see that these lines comes from the down deep area up to the trench. So this is roughly a Valdivia-like earthquake. And then you have these lines that goes from the down deep area to some portion of the seismogenic zone, which is Melinka-like ruptures or Chilean-like ruptures, resembling this earthquake right here. So we look deeply at those events, and you see here two of representative ruptures that occur. So for the Chilean rupture, you see that it starts in the down deep, then it propagates at some portion of the seismogenic zone. And for the Valdivia earthquake, you see, interestingly, that when it reaches this line, which is basically creep caused by the stress concentration at the deep of a previous rupture, like this one, it takes advantage of that to keep the propagation up to the trench. And then, okay, this is a very nice model, but we compare this with actual data. So we look first at paleoseismicity. So we have a very good record of paleoseismicity in southern Chile. And you see that this dashed line is basically the mean value of the paleo recurrence times for earthquakes of these characteristics. And then you have the paleo recurrence time for very large ruptures right here. So these violin plots are basically the distribution of the recurrence times of our simulation. And you see that, assuming all that I showed you before, we get roughly the distribution of the paleoseismicity. Then we look at the pore pressure ratio. So this is the upper seismogenic zone, the lower seismogenic zone, and then the creeping zone below the mojo. So you see that if we assume that the pore pressure ratio is lower in the upper seismogenic zone, the root mean square error compared with a lot of data that we compare with these models is decreased. And the same goes for the lower seismogenic zone. If we increase the pore pressure ratio here, we decrease the error. So we are finding the same relationship that Marcos found in 2018. And then we look at surface deformation. So here the data of Plafker and Savage that they took 8 years after the Valdivia earthquake. And these are basically the same distribution of the simulated ruptures 8 years after they happened. So this is a combination of coseismic and post-seismic deformation. And you see that we changed the composition. So let's say that there is no subduction channel in southern Chile. You get that we are not able to reproduce the surface deformation measured by Plafker and Savage after the earthquake. And what happens if we change the length of the seismogenic zone, represented by the W value right here? You see that the deformation pattern is shifted landwards. The same goes for coseismic slip. It shifts landward for the case of the more small ruptures. Well, then you have the example of northern Chile. And this is the same cross-section that I showed you before, but interestingly here, it has been very well studied that before the Ake earthquake, we had a precursory phase that started with an 8-month slow slip event. Then an upper plate fault was activated, and seismicity migrated from here up to the Megathrust, eventually generating the Ake earthquake in 2014. So we wanted to try the control of how basically an upper plate fault is have a control on the seismic behavior of the Megathrust at this latitude. And we run various models, so I'm going to show you just the preferred one right here. So this is the case of the M2, which is basically the model with the fault. We also run a model without the fault. So with the fault, what you get is this. So you have also very giant ruptures, but you have these partial ruptures located in the updeep that are resembling what happened with the Ake earthquake. And you see that you have a progressive unlock, and something happens before the partial ruptures. So if we zoom into that, we see that there is a precursory phase. We have a seismic slip front. You have foreshock seismicity, and then you have the rupture. So it's similar to what happened with the Ake earthquake. We compared this with surface deformation. So here you have the data from the Ake earthquake and some co-seismic slip models. This M1 is the model without the fault. And you see that without the fault, if you not consider this active fault being there, you basically cannot reproduce exactly the data of the earthquake. And then if you put the fault there, you are able to generate some events that are very close to both the data and the co-seismic slip. So maybe upper plate faulting had something to say in surface deformation and co-seismic slip after these partial ruptures. Finally, you see here the seismicity. 1 month or a few months before the main event. So you see this is colored by the distance to the interface, the normal distance to the interface. So before, during 2013, nothing happens right here roughly. And then you have this increase in seismicity suddenly that eventually ends with the Ake earthquake. So a good idea is to try, well, what if because all these upper cross faults are very close to failure, but they need a little push. So what if this push comes from changes in the pore pressure ratio? So you can induce a short wavelength perturbation right here to change the effective normal stress and thus see what happens.
2 more minutes.
Yeah, with this I went to end. So we did that, and then we compute the distribution of the normalized cumulative seismicity for each case. So we try systematically with different values of pore pressure ratio. And this is the distribution of the normalized cumulative seismicity before the Ake earthquake. So you see when you decrease the pore pressure ratio, you reach roughly the distribution of the normalized cumulative seismicity before the Ake earthquake. So basically the idea here is that you have this subduction zone, you have an upper plate fault that may be activated by fluid release. So you have focus flow right here. This activates, triggers seismicity right here, and then the seismicity migrates up to the megathrust, rupturing in the Ake earthquake. So basically, you dry up the megathrust, which is represented by the decrease in the pore fluid pressure right there, and then you activate this fault, and then seismicity migrates from here up to the Ake earthquake. And that's it.
Okay, thank you. Any questions?
Thank you, very interesting talk. In relation actually to the last slide you showed, so you infer that basically that the splay faults, they mark perhaps the down deep end of the seismogenic zone as being also a release for the pore fluid pressure.
Yeah.
Or would you think of basically the contrast of pore fluid pressure associated with this drainage path being marking this slow sleep versus seismogenic zone condition?
Yeah, not quite, because here faults are entering, delimiting the up deep limit of the seismogenic zone. So this is the outer wedge, and this is not a splay fault, it's I would say something like a backthrust. And this is basically marking the end of, or the beginning of the seismogenic zone. So from here, the seismogenic zone. Yeah, so from here up to roughly 60 kilometers, it's the length of the seismogenic zone. Yeah.
Well, no more, maybe both the top and the bottom end marked by
Yeah, in fact, you have some evidence of that in southern Chile. So in southern Chile, there has been mapping some faults viewing seismic wave profiles, and those faults maybe are reaching at the same depth at which the Mojo intersects. So yeah, people try to interpret that as you have a fault that is delimiting a very big basin where the Chiloé island is. It roughly coincides with the end of the seismicity and with the presence of the Mojo. Yeah.
Any other questions?
Thank you very much. Very interesting talk. So, do you have any ideas about time needed for these fluids to transfer?
Time?
Yeah.
Difficult to say. So maybe if we assume that the seismicity triggered in the upper plate fault is purely due to fluid, that seismicity roughly has started 15 days before the event. So, and then it begins to propagate some days before the Iquique main shock, so I will say some days. Yeah. Yeah.
Any other questions? If not, let's thank the speaker again. Okay, the next speaker is Diego Molina. He will talk about sleep behavior of seismic barriers. Go ahead.
Can you hear me? Yes? So my name is Diego Molina, and today I will show you more or less what I have been doing during the last couple of years. That is related to the fact that I'm exploring the nature of trying to understand the nature of seismic barriers. So as you might know, we have this seismogenic zone where you have the nucleation of earthquakes in these asperities that behave mostly in a stick slip behavior, right? They get coupled. But when you have the alone strike propagation, for instance, of these earthquakes, they get usually arrested in these areas that behave as seismic barriers. So usually we are not very interested in what is arresting earthquakes. And so in this work, I'm trying to address what might be the candidates for the frictional behavior characterizing these areas arresting earthquakes. So I will try to show what I have been doing from a numerical point of view, numerical modeling, but also from geodetic observations. So one particular feature of these seismic barriers is usually that you have low coupling in this region that are arresting earthquakes coming from the north or from the south, or the opposite, that is high creeping rates. Okay? So interestingly, these regions also are associated, when you have low coupling, usually to the subduction or important subducting topography. And you see that here, where you have low coupling, usually you have the arresting of earthquakes, so you don't have too much moment released in these regions. And there is a very well study made by here, Mr. Kaneko, that was really inspireful. So he really nicely, in the framework of rain state friction, he tried to understand the systematically how velocity in strengthening region can arrest earthquakes, and he managed very well. So he showed that low coupling or variable coupling can be addressing by these strengthening regions here, sandwiched by these two asperities, and also this earthquake arresting. But there is a particular question. Do earthquakes always stop in regions where the coupling is low? And so it might be not the case. So there are several cases where you have that earthquake propagation are arresting in regions where the coupling is quite high, okay, or intermediate. And this is a bit counterintuitive with the idea of velocity and strengthening behavior. So one of the questions that we have is, can, for some particular reasons, velocity weakening create earthquake arrest? And this is the things that I will try to understand now. And basically what I will show here is that if you are studying the rocks that you expect to find within the seismogenic zone in this range of temperature, you see that many of them indeed behave as weakening, and just some of them could behave as velocity and strengthening. So it might be that velocity and weakening and velocity and strengthening barriers are indeed in nature. But what particular conditions we need to create weakening barriers? So similar to Kaneko, we try to run numerical simulation of the earthquake cycle, assuming a similar tectonic setting. You have two weakening asperities, and in the middle, you have a barrier that is also weakening, but with a few increase in the A minus B value. And for this, we run many simulations, increasing sigma n, normal stress, or the critical distance parameter. Okay? So then I will show here how these velocity and weakening barriers usually behave. So this is a particular nice simulation in the left, where you have the cumulative seismic slip in the x-axis, y-axis, and here you have the position along strike. So from here, you see that many earthquakes in these red contours are not able to propagate through the barrier, although there are some events that are able to propagate through the entire segment. But in particular, in this case, you have the arresting of earthquakes many times, and these are permanent barriers that we're observing. When we calculate the interseismic coupling in these regions, you see that, as you might expect, the asperities remain locked most of the time, and the earthquakes here are shown in blue. So the barrier also, you see that it's very dark, representing that you have a lot of sleep deficit accumulation. But instead of releasing this slip in creeping or a seismic behavior, or just creeping, right? What you see is that the earthquakes are usually triggering after a slip that propagate through the barrier to the other asperities. So yes, the seismic barrier seems to be plausible, locked through the seismic cycle, but instead of releasing the slip deficit through earthquakes, you released the slip by after the slip or slow slip events. And also interesting, you see that the coupling average in the barrier is very variable along time. And you don't need to create frictional properties change through time to create this, okay? So that is a message. If we want to try to understand what is controlling this barrier efficiency, for instance, you have these two plots here, where you plot, where you show here, or you can observe the probability of earthquakes crossing the barrier. So here is bigger efficiency. A lot of earthquakes can be arrested. And you see that this is increasing when you increase this critical distance parameter and also the normal stress, right? And when we compare this with the coupling, so here we have the coupling average in the barrier in my simulations, and I compare with the velocity and strengthening barriers coupling features. And you see that usually the weakening can indeed be much more coupled than velocity and strengthening barriers. But when you really increase the efficiency of the barrier and you decrease the coupling, you need really high values of DC, okay? And this might be not plausible in nature. So in this case, potentially velocity and strengthening barriers, as Kaneko was showing in his paper, are the case. But in nature, how we can distinguish, right, between these strengthening or weakening barriers, how we can try to explain them. And to gain more insights from this, now I will show you, or I will jump into more geodetical observation to study a nature barrier in Chile. So here, this is what I'm doing currently in my postdoc in ISTEG. I show a typical case where there is a reported or identified seismic barrier associated with subducting topography here. Okay, so you see many earthquakes arresting from the south or to the north, and as you see here, you see many lines, and these lines represent many earthquakes or slow slip events. So it seems to be that these barriers are also very complicated in terms of slip mode and slip segmentation along dip and along strike. So in this particular case, I will try to, so also before jumping in that, this region is where we identify these shallow slow slip events that Anne was talking yesterday. So we have this very strong segmentation. But in this talk, I will focus more in these deep slow slip events that you can see here in red, that after this ongoing seismic deformation was interrupted by a shallow earthquake that happened in the nervy side of the ridge. Okay? So here is the main results from this, just to show you or to emphasize that these seismic barriers are very complex in slip mode. So you see the time series for the slow slip event, for the 2020 slow slip events, and what I did was try to understand the slow slip rate in the initial part, during the earthquake, and after the earthquake. So initially, we also identify in these black circles seamounts that are associated to the ridge subduction. So you see first that the slow slip event seems to nucleate or initiate within or in the edge of a subducted seamount, and then after 6 months, you have the nucleation of this earthquake here. As you can expect, you have the after the slip propagation, and this is arrested now for this shallow seamount here, but also you have an increase in a slip rate in the same region that was ongoing slow slip events. And finally, you see that after this shallow sequence, you have this migration of the SSE towards north. So we compute column stress change to try to see if there was some kind of static triggering between these different phenomena. And we see that there are not many changes or significant changes. So we attribute this potentially to dynamic triggering that caused this acceleration of the slow slip, but in a region that potentially is fluid abundant, that makes the fault to be more sensitive to small stress perturbations. So we have evidence for fluids. So here I show you first, try to characterize the structure of this barrier associated to the ridge. So here you have the two seamounts associated to these anomalies. And we perform some tomography along this profile, and you see that the regions between the two seamounts is highly hydrated, or characterized by high BBS. So interesting, the seamounts themselves seems to be drier, okay? And this can have many explanations, but so far what I want to emphasize is that we have a lot of hydratation in this region. And another particular thing that Joaquim was mentioning is that in the northern part of Chile, we have sediment or a trench sediment starved. So potentially wet sediments coming into the interface are not supplying too much fluids into the interface. So the sources might be other, and this is what I want to show in this more or less final figure. So what we believe is when you have a ridge or we have seamounts, the load makes much more fracturing into the sonic floor, right? So you allow much more percolation of seawater, and that is resulting in alteration of these rocks. Another feature is that the seamounts themselves represent much more volume of rock to alter it, and results in this very variability of clays or chloride or minerals that are hydrous minerals. And particularly also, these seamounts or these materials behave, as you see, mostly in velocity and straightening behavior. So it might be that when you have along strike important features subducting, you are creating important heterogeneities between weakening or strengthening that can explain all these variabilities together with the fluids that are potentially being expelled because the ridge themselves has been much more hydrated and altered. And then after going into metamorphic reactions, is able to release much more fluid compared to lateral zones along strike. So just to finalize, more or less, or to sum up, what I have been trying to say is that potentially these regions where you have low coupling are associated, and that usually are associated to this subducting topography anomaly, are being characterized by velocity and straightening material due to this alteration of the seawater that is much more easily to do because it's much more faulting or fractured. But when you have high coupling, potentially these other kind of barriers are associated to velocity and weakening behavior, and these heterogeneities within this framework associated to higher normal stress or critical distance parameter might be caused for upper plate features like a strong heterogeneity and density that increase the load in the interface and is able to create this earthquake arrest. So yeah, that has been my talk. And if you have any questions, I'm happy to answer.
Yeah, any questions from students maybe first? Yeah, Tama.
I have a question that the velocity weakening barrier is only for the subduction zone, or sometimes it can be applicable for the inner aspect as well?
No, it's just in the subduction zone so far. So I did just an analysis strike trying to numerical modeling.
Did you need a two-step weakening barrier, or if you do a profile, a continuous profile, just weakening in the middle and more weakening in the middle and then weakening again, it works the same?
Oh, can you reformulate the question?
Okay, you have two weakening barrier in the middle of two patch of weakening, right? Does it work the same if it's a continuous weakening but just not stepwise?
No, it seems to be that you need a bit decrease in the weakening behavior. So I minus B a bit higher, but still weakening.
Yeah, that was a wonderful talk. Right, you started out showing Yoshi-style models, and you can make this very complicated behavior with a not very complicated model set. So now, with your last slide, right, what will your next model be? Will you put in these?
Yeah, so... Yeah, so my idea is try to model this behavior. So similar to Joaquin and what Sylvain might be doing also is try to characterize first what minerals and what kind of rock are we expecting in these seamounts or in this ridge. But also try to change the pore fluid pressure because probably we have a lot of dehydration. So also I would like to try to use these thermal models to constrain where metamorphic reactions are more probably, and to see where probably fluids expellation is more probably. So yeah, I would like to combine this straightening behavior, fluids that usually also has been trying to do, but also increasing damage because the ridge is creating much more damage with respect to these lateral zones.
Hi, thank you for the talk. So there are some lithological variations in the polar from north to south, and this will change the normal stress. And how you compare what we know about geology in the polar and
Yeah. So basically, what I have been doing so far is that in North Chile, in some places you have more volcanologic or units, right? And also metamorphic. So with Andres in Chile, we try to estimate the density associated to this rock. And when you have these lithological constraints, based on the density, try to calculate this vertical normal stress and from that normal stress. So I really think that the upper plate also is having an important role here, and it seems to be also needed to model.
Yeah, you're using friction, and I guess it's also a question for the chairperson here. You're using the rate-density friction for your modeling barriers and during the seismic cycle. Is this, do you include dynamic weakening? Because we know dynamic weakening, whichever rock you slide fast will weaken very dramatically, very quickly. And is this included in some of your models? And if not, what do you think would be the impact?
I don't remember this. Maybe Jean-Paul, you know if it was included? I don't. Oh, yeah?
Well, first of all, his model is quasi-dynamic, so
yeah.
The inertial effect is not good. I did include inertial effects, but the challenge of dynamic weakening, as mentioned in Roland's talk, is that you have to kill dynamic weakening to arrest rupture, because either through the shear zone thickness or some other complicated assumptions you have to make. So of course that's shown to be important in lab experiment. Whether it will be applicable in nature with the heterogeneity and things like this, I think it's an open question. Very good point. So the two more questions.
So I'm confused by the idea of the seamount inducing more water in the crust. Is there any other, because there is plenty of water in all the minerals that are forming the oceanic crust.
Yeah.
So I'm not sure that's needed. So is there any other evidence, like external stuff that could help? And my second question is that your VPVS image is really impressive, but you could also argue that where the seamounts are is also where you have less anisotropy. So
yep.
Not sharp, not as large VPVS ratio as well.
Yeah. So first, the first question.
Unrelated to fluids. So how do you argue against that?
So first, the initial question is, yeah, it's true that the entire oceanic plate is being altered. So what I'm saying here is the seamounts, when you have very prominent oceanic relief, more seamounts and these ridge and plateaus, the amount of rock that you are altering is bigger or larger compared to lateral zones. So the amount of hydrous minerals that you are altering should be higher compared to these regions, lateral regions. So you will increase the fluid budget when you are going into subduction respect to lateral regions. That's basically the idea. And also you are creating much more faulting and fracturing where you have the seamounts. So you percolate much more easily seawater and alterate much more portions of the slab. That's more or less the hypothesis. That's something that we need to test.
Yeah, that's what I meant. The hypothesis. So is there any way you can prove that in a different way?
It's something hypothesis that came out this week, so a few weeks ago. So I think it's something that is still ongoing. It's ongoing work. So I will think about it.
Last question. Diego, very nice talk. Thank you. Just adding to the discussion and the point that was made here about extreme dynamic weakening. And we heard earlier in the week a beautiful talk about extreme dynamic strengthening by dial latency. So
Yeah. I think another thing that probably we can model it, and I think there are people working on this, instead of having straightening regions, is this dilatancy straightening that we also potentially, and we don't need weak straightening for this, just weakening. But yeah, it's something, another opportunity to model this. Yeah, thank you.
Right, great. Let's thank Diego again.
Thank you too.
Morning session, second part of the morning session. The session theme is theoretical framework, and first speaker is Brittany Erickson from University of Oregon.
All right, can you guys hear me? All right, today I'm going to be talking about forward modeling of earthquake sequences with rate and state friction, and I sort of been piggybacking on my own talk and adding some stuff on inverse problems as well. I have a lot of work to show here, mostly done by my students and also with my collaborators. So thank you for the organizing committee for inviting me. I don't know if Yi is here, but she emailed me last spring and invited me to give a talk, and I said, I'm very pregnant, I don't think that's a good idea. And she said, you can totally do it, I'm positive. I'm very confident. So I don't know if that's true or not, but it remains to be seen. So in my talk today, and I'm going to actually set my timer because halfway through I want to make sure that I get to the latter part of my talk. Sorry. Set it for 25 minutes. Okay. So the first part of my talk, I'm going to discuss some science driver questions just to motivate my results and my work. I'm going to discuss lots of different types of approaching modeling of earthquakes and then put my work in that context. I want to talk today about some of the computational challenges that the community modelers have dealt with. And this is all a focus on traditional methods for earthquake modeling. I'm going to talk about progress we've made through 3 problems in community benchmarking that we've done. And the latter half of my talk, I'm going to talk about physics-informed deep learning for forward and inverse modeling as opposed to traditional methods. If you were at my SCEC talk in September, you'll see some of the same material, but I only think a few people were there, and I found it important topic to discuss. So I'm going to talk about physics-informed neural networks, and then even if you were at my SCEC talk, you can check your email during this part. And then if you can come back down here when I share my random thoughts on machine learning, that would be great because it'd be interesting to get your thoughts on that. So some science driver questions. So the National Academy has recently put out a report stating very specifically what is an earthquake. And they said, we sort of have an idea of how what equations model the subsurface, but we don't really understand constitutive laws at depth. We want to get towards predictive models. Part of that is an understanding of earthquake source processes, rupture features, and also how does fault slip history influence subsequent events, which will lead me to my discussion of earthquake cycle modeling. We also want to improve the predictive analyses of seismicity and ground motion, and this was put forward recently by the SCEC research plan, combining physics-based machine learning methods. There are persistent challenges, as we've seen. Largely, direct observations of an Earth's interior are inaccessible for the most part, and great earthquakes are infrequent. So we have lots of capabilities for obtaining surface deformation, but they are confined to the surface. So there's different approaches to modeling earthquakes. There's the spontaneous dynamic rupture simulations over here versus earthquake simulators, and then after this slide I'll talk about earthquake cycle modeling. So dynamic rupture simulations model a single event earthquake rupture. They've been worked on for decades now. They're very advanced. They've gone through successful verification and validation efforts, and they are, they are limited in the sense that they have to assume an artificial pre-stress condition and ad hoc nucleation process to get the earthquake going. But after that, they have, very strong capabilities in sort of obtaining those fine-scale features of wave propagation. The earthquake simulators, on the other hand, are able to simulate millennium-scale seismicity patterns in very large fault systems. They do assume a quasi-static approximation, and they do simplify interseismic loading to allow numerical tractability. So there are these 2 types of earthquake modeling here, and then there's a third type which I work on, which is the sequences of earthquakes are in an aseismic slip, or we've deemed it seas. And I'll give more of a historical perspective on this group and where it's come from near the middle of my talk. So seas simulations, aka the seismic cycle, are now prevalent in lots of earthquake research. They address key scientific goals. But the idea is that we start really simply. So I've been attending this conference all week. We know that faults are really complex. Fault structures are really complex. The materials surrounding faults are really complicated. The fault geometries are really complicated. But our goal here is to start with the simplest possible modeling scenario and then study it in a really rigorous way and really fully understand the numerical methods and what their limitations and capabilities are. So we assume a planar fault embedded in some medium here, like for example in a homogeneous elastic medium. Our input into the model is the fault geometry, material, fault friction, and bulk rheology. we send those to computational methods for simulating earthquake sequences and then try to connect them to observables like ground shaking and aseismic deformation. So this is just one example from Zhang Lapusta, and we've seen this earlier. I think Roland had a similar video in his talk. But this is an example of a code based on the boundary element method, where they only have to discretize the fault interface itself. And these have been well developed in the sense that they can study 3D fully dynamic models with generally within a homogeneous elastic medium, although there are ways to include viscoelasticity like Sylvan's code. They're very efficient at solving 3D problems. They consider post-seismic stress relaxation and microseismicity and allow for the comparison with data. Alternatively, you can do a volume-based SEAS model, for example, one based on the finite element or finite difference method. That's what my group has been working on. I'm showing slip profiles here for some of our work with a quasi-dynamic method. There are also methods for doing fully dynamic earthquake ruptures with a volume discretization. These volume-based methods are not as efficient as the boundary element-based methods because you have to discretize the whole volume, and those can lead to very large systems of equations. But when you do that, you can include heterogeneous bulk material properties, for example, sediments or off-fault inelasticity really easily. And you can also incorporate fluid processes if you want. So these are some slip profiles from some of my work over the years. For example, earthquake sequences within a homogeneous elastic medium versus the sedimentary basin, where you have a basin depth of 8 kilometers and you see smaller earthquakes that nucleate and can't penetrate up through the basin, and then they're followed by surface rupturing events. We also looked at bulk inelasticity, and I'll talk more about this later, but with bulk inelasticity, you see a percentage of the tectonic load accommodated by damage rather than discrete fault slip. And so we had some analysis in our 2017 paper related to understanding the shallow slip deficit as part of that inelastic strain down here. So I'll talk more about that during my talk. I'm not going to really discuss rate and state friction. We do use one of the most simplified laws here, either the Dietrich or Rumina law down here for state evolution. So fortunately, others before me have described this better. There are persistent computational challenges in the sense that earthquakes aren't standalone independent events. They depend on a long history of seismogenic cycling. There are multi-scale features in space and time. There are unknown initial conditions. Prior to a large earthquake, we don't really know the stress conditions at depth. You have geometrically complex fault interfaces and boundary conditions. Fault friction itself is nonlinear, and rate and state friction in particular can introduce numerical stiffness into your method, into your problem. There are also heterogeneous nonlinear media that need to be accounted for in a numerical model, and one of the challenges is that even except in maybe the most simplest case here, there are just unknown analytic solutions. So we have nothing to compare our numerical results to. So how do you model the earthquake cycle? Well, you can start simply with, for example, this 3D model from Rice 1993, where you have a vertical strike slip fault embedded in a homogeneous linear elastic media. You have a free surface up here. You have some slip rate imposed at depth and a rate and state fault up here with variable frictional properties. I just decided that because we were at a school and that I should give some background, that I would talk about governing equations. Mikkel already did some of this in his talk, but we have momentum balance, of course, here, material density rho, a vector of particle displacements in the stress sensor. So this is how we model an infinitesimal piece of the solid Earth over here. And then you need to give it some constitutive law. So for example, if you assume you have a linear elastic medium, then you just have Hooke's law where stress is proportional to the elastic strain, and I'm using summation notation. And C here is your fourth order elasticity tensor. You have a strain displacement relation. And if the material is isotropic and homogeneous, all these equations reduce to the elastic dynamic wave equation. So this is a partial differential equation that is solved. And lambda and mu are constants that correspond to the lemme and the shear modulus. And so 5 here is solved in a lot of earthquake rupture codes. So here are some of the numerical challenges. This is my favorite slide. So wave speeds in the Earth are around a few kilometers per second. The CFL condition attributed to these three people, says that if you're using an explicit time-stepping solver to solve, say, the elastodynamic wave equation, then the wave speed times the time step you use divided by the spatial step has to be less than 1 for numerical stability. Now, if you bring delta x and delta t to the other side, what it's saying is that the physical wave speed a has to be less than like the numerical wave speed. So if you're like integrating numerically, you can't sort of let the wave front get away from you numerically. You have to tract it, or it will go unstable, and your whole method will blow up, and you'll see nans. It's not what you want. Okay, so we have this limitation on the time step, given a certain spatial step. That's how you should think about that. So ideal grid resolution is 10 meters. I mean, probably even smaller. Ideally, right? It's way, way small. But let's say it's 10 meters. This requires a time step on the order of 1/10,000th of a second for numerical stability if you take the wave speeds to be 5 kilometers per second. Sorry. So for a domain size of 100, hundreds of kilometers, the number of spatial nodes is in the billions, so sad face. Rate and state friction, so in addition, introduces numerical stiffness. Numerical stiffness simply means that the time step needed to maintain stability is much smaller than that needed for actual accuracy. It's just an annoying feature of some problems. So we have that to deal with. Another way of thinking about stiffness is that explicit methods tend to just not really work. You have to use an implicit time stepping method. And then also inertia. So one way around this is that inertia is often approximated so that we only have quasi-dynamic earthquakes. And this does mean that you can take large time steps during the static phase because you don't have waves. You don't have to worry about the CFL condition, and that's what we tend to do in these. Well, this is what we did in these early methods here. So the first case here is overcoming the time stepping example. So I'm looking at a vertical cross section of that 3D Rice model. So the rate and state fault now is this vertical line right here, and we have motion in and out of the plane. A governing equation is the wave equation for antiplane strain. And we need to solve one for the unknown material displacements u. The CFL condition means it's impossible to do cycles, so what we're going to do instead is we're going to assume that at least during the interseismic period that inertia is essentially negligible. And we're also going to approximate it during the coseismic phase, and just assume it's still negligible, but account for the shear stress due to the coseismic phase by adding on radiation damping to our constitutive law. So we discretize our domain. So this is just a schematic of a finite difference grid. You take all your spatial derivatives and you just approximate them with fractions, basically. So you add up a couple of nodes around you and divide it by your grid spacing squared, and that's an approximation of the second derivative. And you plug all of these finite difference approximations into your PDE and then try and solve those equations. So we generate cycles of earthquakes by loading it at the remote boundaries at a slow plate rate. You could also load it below the fault if you wanted to, down here. And we take free surface boundary conditions on top and bottom. We load it. The fault will be frictionally locked right here until an earthquake nucleates. So rate and state frictional fault. Once you discretize it, you end up getting this large linear system that you have to solve at every time step n. So this is basically, this is some large matrix A. It's a sparse matrix. It stores all the information on the PDE. B stores all the boundary conditions, and then U is your unknown displacement everywhere in the domain. So it's AX equals B. I have told my students repeatedly that people will spend their entire lives solving large AX equals B type problems, and they didn't believe me until one of my students graduated and got a job in industry, and all he does now is solve AX equals B. So this is a simple linear system of equations on which careers are made. Okay. The linear solve takes about 99% of the computational work. So you can do adaptive time stepping now and integrate quickly through periods of slow tectonic loading and quasi-dynamic rupture, and you can generate these cycles. So we've seen a lot of images so far of slip profiles, and nobody's explained them yet, so I'm assuming everybody knows what they are. But if you're not quite clear on how to read them, let me know. It took me a long time when I was a graduate student to understand that, what I'm going to be looking at here is so I have fault slip here. So if it's greater over here, then I have some like loading happening down here, but like it's locked up there. And so that's what those slip profiles look like. So for example here, right, in the beginning, the cumulative slip is 0, and you get interseismic loading down here. So these slip profiles are plotted in blue every 5 years during the interseismic period, and then every second in red during quasi-dynamic rupture. And so what's maybe not clear here is that the reason why it's white right there is that it's just a feature of the plotting device that you choose, but there's actually post-seismic afterslip happening in those regions there. And then you get little earthquakes that are nucleating at around like 9 kilometers depth or so. So it's just a simple homogeneous elastic simulation. If you add a sedimentary basin, so if I go back here to my schematic and I look at a sedimentary basin, so just looking at a basin of depth D, of width W over here, we want to understand how material heterogeneities affect that earthquake cycle. So what you get is, so I'm looking at a basin depth of 8 kilometers, 8 kilometers here. So the basin depth is around right there. And what happens is that the earthquakes still nucleate below the basin, but they have a hard time penetrating up through it. And so what we found, though, however, is that you could get a couple of events that were called sub-basin events, and then they were followed by a very large surface rupturing event right here. So this is from a paper from 2014, and so we speculated at the time that maybe the shallow slip deficit that we were seeing was really because we were seeing a bunch of sub-basin events that weren't able to penetrate through sediments, and that it was just a feature of being not part of the cycle, and that we would expect to maybe have that slip deficit overcome by a large surface rupturing event. So you can talk to me more about that in the discussions I've had, and if you want to come find me. Overcoming the elastic assumption. So one of the other numerical challenges is that the real Earth is not linear, homogeneous, elastic. So we saw a really good talk this morning about the complexity of these fault structures. And Skeck also put forth a question a few years ago on what is the role of this off-fault inelastic deformation on strain accumulation, dynamic rupture, etc. It's very poorly understood. So how do we bring this into a numerical method? So Sylvan asked a good question this morning and said, how do we basically bring this to our modeling? And I don't have an answer for that $1 million question, but I do know, okay, so what I can say is that, the stresses generated in most of these elastic earthquake models exceed the known yield criterion for most rocks. So we do need to incorporate this somehow into our modeling. And Drucker-Prager is one of the most commonly used plasticity laws in earthquake modeling. I could not tell you if that's a good or a bad choice. Yihe has another, she showed another model on Monday. And so this is a model for soils. And it basically says the following. It says that it gives you a constraint optimization problem. So you have some stress tensor. You can diagonalize it. It has 3 real eigenvalues called principal stresses, and if you plot those, and if you look at those principal stresses and you put those on your axes here, you can plot the yield surface of the Drucker-Prager rule, and it says the following. It says that okay, so this stress tensor has some invariance. The trace of a matrix, is invariant under your choice of basis. J2 relates to the deviatoric stress here, and it just basically means that in principal stress space, your yield condition is a cone. And other types of plasticity laws say the yield surface is just a different shape. So if you're inside this, if your stress state lies at some point inside here, then you just respond elastically. And if you land on the surface itself, then you're deforming plastically, and you cannot exist in a stress state outside of that cone. So the plastic ingredients here, you have to have a plastic flow rule that says your plastic strain, how it evolves in time. So there's a dot up there, and it's related to the equivalent plastic strain rate, lambda, and a second order tensor that involves like dilatancy and things like that. And then you have a yield function f that just says that you have to either be on or inside the yield surface. And there's some persistency and consistency conditions that just state that if you sort of land on the cone itself, you have to persist on there for some amount of time. computationally what it means is that if you're time stepping and you're in some stress state at time n, and you integrate one step and you somehow land outside of this, we call this a sigma star. We say this is our like elastic trial stress. We assume that maybe we're just going to respond elastically, but oh crap, we landed outside of the yield surface. So there's a return mapping algorithm that says, okay, there's a way to actually project that right back onto the yield surface, and that's your final stress state at time n+1. So this is all from this computational inelasticity book that I read throughout my postdoc, essentially. So what happens then is that if you want to look at the constitutive relation, you can still relate stress to total strain, but your relationship here has to do with now what's called an elastoplastic tangent stiffness matrix. So it's not the elastic stiffness tensor we all know and love, but you can still relate stress and strain together as long as you do it through incremental relationships. That's why those D's are in front there. And the other problem is that before, in an elastic scenario, this tensor C is constant, but now it's actually a nonlinear function of the stress state yourself. So now you're like, I just wanted to introduce some sort of plasticity or like ability to look at damage, and I've done all this sort of this simple model, and it's already like very complex and very nonlinear. So I'm going to go back to moving beyond the elastic assumption here. I'm going to go back to my 2D antiplane strain problem. This is just momentum balance right here. But if I substitute in Hooke's law, then it's actually, I need to incorporate, this should just be elastic strain. So it's the total strain minus the plastic strain. And then my plastic strain evolves according to the plastic flow rule, and I'm replacing everything with an incremental relationship. And what I end up getting is this equation 9 here, which is just, it's a 2D elliptic problem, so it's also going to give you some AX equals B scenario. But these coefficients in front now are nonlinearly dependent on your stress state. So again, we're going to discretize everything with finite difference methods, which basically means you can replace all partial derivatives with a matrix. You end up getting another very large system of equations now for the increment and displacement. So before I said it was 99.9% of the work. Now it's 99.9. This is an estimate. The amount of 9s you put here doesn't matter. It's a lot. Because A now, it's stores all the information about the physics of your problem, but it's no longer constant in time. So you can't like factor it once and then reuse it in the time-stepping simulation. So very expensive. This again is just our elastic reference, and then we want to see what it looks like once we include plasticity. So this is hard to see too, and Yi showed some simulations like this too, but plasticity is mostly going to take effect up near the surface of the Earth, near the free surface up here. So in this shallow region up here, you can see that the slip profiles are getting sort of less and less. So there's more of a slip deficit occurring up near the surface with every earthquake. And if you look at the plastic strain accumulated, so now what I'm plotting is the fault is now here. And it's sort of in between this flower structure, and I've just zoomed into it, so I'm looking at distance off the fault through the different events, and you can see this flower structure of, I'm plotting equivalent plastic strain up here that's broadening and spreading outwards with each event. So by event 18, you see a very large damage zone that's concentrated around the center of the fault. Okay, so that was overcoming the elasticity challenge. Now I want to look back at reintroducing full elastodynamics. So up to this point, all of the simulations have been quasi-dynamic. So we want to actually have waves. So my students and I revisited these quasi-dynamic simulations of Erickson and Dunham from the 2014 paper, and so we want to actually add full dynamics to this case. And so we developed a new method that incorporates full dynamics. We have to have some grid stretching here in order to make it computationally tractable. So we put lots of resolution near the fault itself and up near the surface where the basin is. We're looking at a rate and state fault again with depth variable parameters, no aging law, just Dietrich law, incorporating a switch to fully dynamic. So we still have the difficulty that we can't include full dynamics for the whole simulation because of that CFL condition. So what we're going to do is we're going to assume that inertia is negligible during the interseismic period. And then at some point when an earthquake nucleus, we're going to be like, okay, something's happening. I'm going to now switch back on inertia. And I'm going to actually switch to a fully dynamic method. And I'm going to take a constant time step because I'm limited in that region to the CFL condition. Now, I said that the time step needed was like 1/10,000th of a second. Well, you can't use that for hundreds of years, but you could use it through, through one earthquake that maybe lasts 30 seconds or so. So our computational framework for this is we looked at we use a type of method based on SBP stat, which is basically a type. It's very similar to a type of fun element method that involves a provably stable discretization and some sort of advanced techniques for imposing boundary conditions. We have complex fault geometries now in this with material and frictional heterogeneities, bulk and elasticity. We've been targeting the SEAS earthquake cycle simulations with full dynamics. These are just some simulations from one of our papers where we had a circular fault here, and we were really just figuring out if we could resolve the waves that propagate through this frictional interface well. And once we did that, we were able to move on to actually looking at the earthquake cycle. So I'm including this only because I made it, but it's an earthquake is going to nucleate down here. You'll see the two rupture tips, one propagating into the velocity strengthening zone and then one propagating into the basin. So there's a basin here. You can see that the wave speed slowed down significantly, and then you get lots of reflections off of that basin wall, which is cool. So you have an earthquake now propagating. Waves that are emitted from the fault. How do you decide when the earthquake is over? So at some point you say, okay, the earthquake seems to be over. I should probably switch back to my, like static phase where I'm disregarding inertia. And that's a challenge too, is this sort of understanding when to switch. So there's lots of, there's a couple of different ways in which people using volume-based methods have decided to switch. So there's a switch based on maximum slip rate, which we do. And there's a switch based on a non-dimensional R, which is a ratio of radiation damping to quasi-static shear stress. And basically what you want to do is you don't want to you don't want to switch to dynamics too early, because then you're like taking really small time steps but nothing's happening. And once the event's over, you don't want to switch too soon, because you want to make sure that you let all those waves propagate and sort of, die out before you switch back. So we played around with switching based on the maximum slip velocity, which seems pretty good. If you look at the blue line, it's switching too soon, and then if you switch with lower and lower thresholds, they tend to converge to some nice results. Okay, so I'll try and go through this quickly. So these are the quasi-dynamic events for a 4-kilometer deep basin. So I showed this to Nadia Lapusta, and she said, well, the only reason that they're not propagating up there is because you don't have dynamics. And if you threw in dynamics, they'd all be surface rupturing. I said, okay, well, I'll just run it and see. And the idea here is that, if you have sediments up here, we want to know, like, how easy is it to penetrate up into those, like, sedimentary regions, particularly, like, subduction zones, for example. And is it really possible to, penetrate through soft sediments, with just full dynamics? And here we're showing, like, sediments can be a barrier to rupture. So the question is can we go there faster? So this is a fully dynamic simulation of the same thing, and you can see actually that it doesn't go all the way up. So even with full dynamics present, right, you still get sub-basin events. So basins can still form barriers to rupture. And I'll go a little bit quickly through these because I want to get to the last part of my slide. But I will say that if you have, so R is a ratio between the shear modulus on the outside of the basin and the shear modulus within that. And so if you look at quasi-dynamic versus fully dynamic, you can still get sub-basin or buried ruptures with full dynamics. But if that ratio is smaller, then actually all of the dynamic events penetrate through, even if they don't with quasi-dynamics. So full dynamics can allow you to penetrate through regions. It just depends. And I'll say also before maybe moving on is that it really depends on the history of seismogenic cycling here. So if you looked at, if you took the initial conditions, say like at the slip profile right here, and you just looked at one single event and you did full dynamics, it would penetrate all the way through. So it really does depend on the stress conditions left by that history of seismogenic cycling and whether or not earthquakes can penetrate through these regions. Again, this is a quasi-dynamic versus fully dynamic simulation where you have a much deeper basin, and you can see that it's still just, you know, it acts as a barrier to rupture. So I'm going to switch, I'm going to skip these slides. I'll say that yes, we did solve them correctly. But a lot of this is done through progress of community benchmarks, which I don't have time to talk about, but if you want to get involved in this, please let me know. Myself and many others here are involved in the community benchmarks for sea simulations, and we've done a lot of community work in order to basically ascertain whether or not we've been solving them right. And we're also starting community benchmarks with Crescent. So let me know if you, you might recognize some of these people here. All right, so I'm going to switch gears now. I'm going to skip that because I sort of summarized some things so far. I want to switch gears to talk about explosion of deep learning and seismology. I wasn't going to talk about this, but then I don't know, there's just some things that were like keeping me up at night, and I don't know, I was just excited to talk about this. So so explosion of deep learning and seismology. So, you know, we know that machine learning excels in the presence of large data. These neural networks are very common, and you've probably all seen pictures of them. And the idea is that, you know, instead of using sort of the traditional methods like finite difference, finite element, boundary element, maybe we can just use a neural network to solve these PDEs or, you know, understand complex patterns better. This is a historical perspective. So artificial neural networks were developed to mimic neurons in the human brain. And the idea is that the neural network could learn from data and experience. You have some input layer, a bunch of knobs you can turn. They give rise to a loss function that you try to minimize. And if you tweak these knobs enough, you can get a surrogate model of some biological or physical system. So the network is trained so that the outputs are known to close data. Known data. So neural networks don't impose physics in and of themselves. So in the case where this neural network is only data-driven, this loss function is usually defined by like some inputs and some some outputs and some target data. So there's been lots of discussion on how can we introduce physics into this type of model. So there's been lots of recent efforts to integrate physics into neural networks. So the first option is that you can train it on outputs from a traditional method. For example, finite difference. You can run a bunch of finite difference methods, get a bunch of data, train a neural network on that, and then hope that it predicts something meaningful. I've been working on PINs, these physics-informed neural networks, where the data is simply what are called co-location points, which I'll describe, but it doesn't require any alternative method for a forward problem. There are other physics-based deep learning methods, but I don't have time to talk about them today. So the physics-informed neural network is essentially this. So they arose out of the successes of deep neural networks that were just driven by data. They wanted to have something consistent with physics. So they said, okay, I'm going to take my neural network. So this is an example of the equilibrium equation in 2D for this illustration. You have some spatial points that you send in. They get propagated through this neural network, which I'm going to describe also, but these sigmas here are nonlinear activation functions. Basically, because if you don't have nonlinearity in your problem, you're probably not going to have a very good model. You get some output of displacements, and then you send those to differential operators. Those help you compute stresses, and then you compute a loss function. So it could be, for example, that these sigmas don't really equal F1 if you take their derivatives. So that's what your loss function is. See if this is working. I've always, I included this in my SKEC talk because I found myself getting frustrated by talks on machine learning where nobody ever described what they were. So if you have some vector that's an n-dimensional vector that's your input, then you form the first, like the initial layer from that input, and then you multiply each layer by a weighting matrix, a bias vector, and then you compose it with a nonlinear function to form the next layer. And you just keep doing that recursively. And then your final output forms your neural network itself. The phis down here are a collection of activation functions. So again, these are the nonlinear parts of the neural network. And then the weights and biases are your trainable network parameters. So those are like the knobs that you get to turn. You also get to choose how many layers you want, how many neurons per layer you want. There's a lot of different knobs that you can turn to get a good model. The PIN extends the feed-forward network by considering physical laws described by a parametric PDE. So I'm writing it in this form, and I'll explain why later, but you can write a PDE using a nonlinear differential operator L, which acts on U with parameter lambda. For example, if you're looking at the acoustic wave equation and say one, or I guess any dimension here, acoustic wave equation, that should be a second order temporal derivative, minus c squared times the Laplacian. So this lambda is your parameter, and it's just the coefficient of the problem you're solving. TLDR, the cost of the loss function is defined by taking this nonlinear differential operator and plugging in n, which is the output from the neural network. Okay, the general representation of the cost function is basically just a sum of mean squared errors. So you can have mean squared error at, say, any known data points that you might have, and also mean squared error from the trying to satisfy the differential equation itself. And data could be observables or boundary data or both. So if we look at PDEs in two contexts, right, we solve them in terms of forward problems versus inverse problems. For forward problems, this is data-driven inference, so you assume that the parameters of the PDE are known, but you need to find, say, the displacement, versus an inverse problem where you might have some information on the displacement, but you try to learn the rest of it, and you try to learn the coefficient of the problem. So for example, inferring for wave speeds or something. For forward problems, we have traditional methods like the ones I've talked about so far. There's been tons of work in this area for decades, right? It's all AX equals B. For inverse problems, we have traditional methods here, like for example, Bayesian methods that require many forward runs, and there's lots of work here too. For pins, however, can solve both forward and inverse problems, and the nice thing about pins is that for the inverse problem, the code is only slightly modified from that of the forward problem. So this is just a history of physics-informed neural networks. It's attributed to a seminal paper by Rassi from 2018, who showed that you could solve really complex physical problems, PDEs, here in this case Navier-Stokes, using pins. And the co-location points here are the blue dots. You're basically just like, this is your data. You get to choose points in your spatiotemporal domain, and those are your data points. You're not training it on any just data obtained from, like, say, a finite difference method or something like that. There's been lots of work done in this area for forward problems, which I'll skip for now. The other thing that Rassi showed is that you could actually recover coefficients of the PDE itself. So they solved the Navier-Stokes equation where they had a predicted pressure versus an exact, and they were able to basically approximate these coefficients, so like 0.999 as opposed to the one that's sitting out there. So you can learn physics using these models. So I'm going to use this figure here because everybody else has shown it, and I wanted to jump on board. Our group was curious to see if we could use pins to explore the depth dependency of frictional parameters. And our motivation is that slip is thought to correlate with depth, the distribution of asperities, for example, in subduction zones. We want to figure out if we can, understand the physical mechanisms for the diversity of slip styles, right? It's important for hazard mitigation. But the frictional properties are largely unknown. So this might be a simplistic view of it, but we wanted to basically figure out if we could infer depth dependency of the A and B parameters in rate and state friction as like an initial study. So our model setup is we posed it as an IBVP, which stands for an initial boundary value problem. It's just a PDE plus boundary and initial conditions. You can pose it like this. And the reason why I'm posing it like this is it makes the diagram look a lot better. But L and B are differential and boundary operators. And for example, if you have the 1D wave equation here with the wave speed c squared and some source terms, then your L is just, again, the second temporal derivative minus c squared times the second spatial, and B is the identity operator. It's just an example of what those look like in sort of a real equation. The general pin architecture we took here are given here. We have one for the volume and one for the boundary. and they both give you a mean squared error for the domain and the boundary itself that add to give you our final mean squared error. So one thing I'll talk about later is that, you know, this is your cost function that you're trying to minimize. And what you do is you just send in a bunch of data points, which are just spatiotemporal points in your domain. You pass them through the neural network, and then you calculate this. You're trying to minimize this. So what you have to do then in order to minimize it is take its partial derivatives with respect to the weights and biases of the problem, and then basically do like a gradient descent type situation, right? That's how you train a neural network. And it's expensive, right? Doing a forward pass, just putting in these and outputting the cost is, you know, efficient, it's fast. It's really the training where you have to, you know, back propagate information in order to train it that's really the expensive cost. So our target is, again, the 2D antiplane, my favorite setup. We looked at the elastodynamic equations. We manufactured a solution so that we actually had some ground truth. In general, you wouldn't have this. And we have an additional connected network for the depth dependency of A minus B. So we're solving an inverse problem in this case. On the left, I'm showing the mean squared error as a function of training iteration. You can see that non-monotonically decreasing. And then over on the right, I'm showing the exact depth distribution of the A minus B parameters versus the machine learning model output from the first iteration in blue, first training iteration, and the 30th training iteration. So you can see it converges actually rather quickly. It's you have to also solve for the interior displacements as well, and that's what takes so many iterations down here. How am I doing on time? What's that? Like slow?
No, you're good. 20 more minutes.
Okay, great.
No, not 20.
Two. Okay, so 10 minutes. Okay, great. So actually, okay, just pull that big hook out and carry me away. Okay, so I want to compare Pin's traditional methods. So some people know this, but I'm very skeptical of machine learning, even though it's something that I study. But I think it's important to have a good level of skepticism. So I'm showing some examples from Seisal, which is a dynamic rupture code out of Alice Gabriel's group that's been worked on for years now. This is a high-resolution simulation of the 2004 Sumatra Andaman earthquake that was shown at the supercomputing conference in 2017. So, you know, this is a traditional method. It's discontinuous Galerkin, I think, Alice? Okay. Got a fault here. You know, it has all of these layers of, you know, heterogeneous material properties. It's got complex fault geometries. It's regularly run on the world's fastest supercomputers. So actually, before I do this, let me talk about some of the challenges. So when you have an earthquake that, say, nucleates on this fault here, you know, there's a lot of computational challenges, some of which I've described already. You know, it's an interface. It's a nonlinear interface if you have rate and state friction. You have wave propagation outwards. For these volume type discretizations, you have computational boundaries. So if the waves hit the edges of that, you do not want them reflecting back. So how do you imitate like an infinite domain? Well, there's ways of doing that, but it's challenging. You have to have what are called non-reflecting boundary conditions out here that are not always perfect. So there's some potential advantages of pins. They are mesh-free, so pins do not have these meshes here. You don't need to discretize with some spatial step and satisfy a CFL condition. You don't need to do that. They might handle complex interfaces more easily. It's stated that they're suitable for ill-posed inverse problems, which we've seen they're capable of doing that. They might be able to learn multi-scale physics. So there's some idea that, you know, in these regions where you know, small-scale features are acting, where you might need more resolution in a dynamic rupture simulation, well, it might be that you could just put some collocation points here and it would actually learn the physics, the small-scale physics there better. Not clear yet. Transfer learning. There's the idea that if you train a neural network for, say, you know, data in some fault region, that it might transfer to another fault region and do some similar, you know, have some similar predictability in that other region. They automatically satisfy absorbing boundary conditions, so you don't have to deal with that challenge. You can solve new problems. So traditional methods in general are confined to like well-posed partial differential equations with you need certain boundary conditions everywhere in order for there to be a solution. Pins don't care about any of that. You could have like random stations up here, GPS stations with data. They don't have to have like the type of resolution you might want. So they might give you solutions to new problems. There's the idea that you can learn the physics itself, so you could learn the coefficients of the PDE like the Rassi paper did. You could also do the deep neural operators, or like trying to learn the PDE operator itself, so maybe it's not the wave equation, maybe it's a little bit more complex than that. These are promises, I'm not stating that they are true. So these are some future directions and possibilities that we're doing. So we're working to quantify computational benefits or lack of when comparing pins to traditional methods for both forward and inverse problems. Grossman has a great paper that says, can physics inform neural networks beat the finite element method? And the answer is no. What's the computational complexity, memory requirements for two algorithms to reach the same level of accuracy, for example? More work needs to be done in terms of uncertainty quantification. So with machine learning, you have an output from a model. It's very unclear how right that is. What have you done? Okay. And Tian, who gave a talk, I think it was 2 days ago, I'm losing track of them, she talked about this idea of dropout, where you can remove neural networks and look at sensitivity that way, and I think that's a really good step in the right direction. The loss function, is it convex? Does it have, do we have a unique solution? It's very unclear. How do we initialize the weights, pick the collocation points? How do you choose the number of layers and nodes? And I don't want to speak for everybody, but I feel like anybody that's done machine learning just randomly picks these things and then just tweaks them until they work. You can tell me later if that's not true. But it's very unclear how to do that. And then how to make sense of output. We want to work on model reproducibility, verification, validation. We need more on uncertainty quantification. There's been some work on Bayesian pins. What we can do in the future, though, for earthquake science is that we can study whether or not we can learn multi-scale processes. Can we use pins, for example, to solve the Skek benchmark exercises? Can we look at sensitivity, right? Like if you wanted to infer depth dependency of frictional parameters using surface data, you could still do that with a pin. And you could do some sensitivity analysis to see, if there are errors in the data, how does, that change the outputs? If there's a different neural network architecture, how does the output change? So there's still work to be done there. I'm going to end with some, I'm going to show you some references on deep learning if you want to learn more, but I actually decided to end with a thought experiment because I'm to the point in my career now where I like giving talks that spark conversation. So I did some math last night, and I'm curious to know what you guys think. So this is my thought experiment. So let's let t-trad be the average time for one forward run with a traditional method, for example, a finite difference method. So say you want to solve the wave equation for one set of parameters, and that's t-trad for traditional. Time tml is the average time for one forward pass through a neural network. Okay, that's just setting your inputs, getting your outputs. I'm going to let capital N be the number of traditional forward runs needed to obtain data on which to train a neural network. So that's again assuming that you have a data acquisition problem. You need to run n forward problems to get the data on which to train your neural network. T-train is going to be the time to train the neural network using data from one forward run. Ideally, you train it with n forward runs, but let's just define T-train to be that. Well, I'm going to state that the time to train a neural network using data from one forward run is some number L times the time to run a traditional simulation. And I know that the training time is more than a traditional time to run a single forward problem for a traditional method. So I'm going to say that L is just much, much larger than 1. The total time then to obtain a machine learning surrogate model, so this is training time plus time to obtain the data, is the sum of these two times, which is approximately the time to do one forward run of a traditional method times the number of data points you want, the number of forward runs you want to do, times this number L, which is the factor, it's the ratio of these two training times over here. Okay, so now let's say that we've done that, and now we want to evaluate our machine learning model with, say, M evaluations of a model. Well, if you have m evaluations of a traditional method, it's just n times t-trad. And if you have m evaluations of a machine learning method, it's just t-trad times n times L. Let's assume that the time to do a forward pass through a neural network is negligible, because that's ideally what everyone's saying, right? We sped it up by a factor of a billion or something, some large number. So let's assume that that's negligible. Then ideally the machine learning time is less than that of the traditional method. We want, let's see, yeah. So we want the machine learning time here to be less than m evaluations of a traditional method. So if you divide through by t-trad, you have NL is less than or equal to m. So for example, if L was 1,000, you need to do 1,000 times more evaluations than the number we train on. So if you have obtained 100,000 forward runs of a model, then you need 100 million evaluations to make it worthwhile. That's just the math that I did. And I'll end with that, and you can argue with me after.
Thanks very much for the clear talk. Any questions from students and postdocs?
Is there a way that BIM can be used for model selection?
Sorry, oh, I can't tell where the sound's coming from in here.
Thanks.
Sorry, can you say that again?
Is there a way that BIM can be used for model selection? So you get data and you take two, for instance, aging law against, I don't remember the other name, and Dietrich again,
Dietrich or Rheology?
Yeah, you do like something, Lagrange constraint, and say, look, this model, give a weight and check if it's possible to say this is a good model for other.
Yeah, and what you could do is, so I mean, when we do these inversions, for example, we have another neural network that solves the state evolution equation. So you could include one for the slip law, Dietrich or Rheology law, and then I guess what you'd be doing is you'd be comparing. You want to use the actual data in the training, right? Like surface data. Yeah, so you could see which one gives you a better model of the surface data. I mean, they're each going to have a loss function that's needs to be minimized, and maybe one is more minimal than the other, or maybe one is like has more like transferability to other data sets. That could be a study.
Any other questions from students? Yep.
Yeah, just a small question. So when you use physics-informed neural networks for like forward problems, and particularly if you have an interface, then like do you see the neural network approximation getting better at the interface, or like neural networks tend to normally give a uniform approximation?
Yeah. So and by the way, like this slide, I'm working in this area, so like I do want to say that I'm just I want to add some discussion to what's possible and what's not at this moment. I'm going to come to your question in a second. I just got sort of sidetracked thinking about something like I forgot to state that maybe the training is amortized, right? So it could be that if everybody is doing these forward runs, say 100,000 or 200,000 forward runs, and maybe that data could be shared, right? And maybe it could be added to, for example, everyone doing it. Maybe over a 10-year period, that initial cost is amortized, so it's like it's worth it to do it in a one-time cost. So, okay, just want to get that out of the way. Answering your question, one of the problems I have with machine learning methods is that you don't see like convergence in the sense that you would with the traditional method. If you train it more, you don't always get closer, and that's frustrating. We saw the cost function decreasing, monotonically, but non-monotonically, but it doesn't go down. Sometimes it just levels out, and you can't get any better even with more training. So did that answer your question? Kind of. You can talk to.
I have one more comment. So if you use like physics-informed neural networks, then the value of n will be 1, right? So you don't need this data.
Yeah, that's a very good point. So you're right. So it still works out the same though. Even with physics-informed neural networks, the data acquisition, so like the 100,000 forward runs, it doesn't actually matter compared to the cost of the training. So it's the physics-informed neural network also has that cost. So again, I think we need to get to a point where maybe we can figure out if that training cost is worth it. And I think it could be, right? But it needs to be discussed.
Yeah, question over there. Yeah.
In the context of like traditional methods, it's a goal to do, for example, polydynamic simulations using elastoplastic considered models of those methods?
Yeah, I mean, I think that's what Yihu is doing. She's doing elastoplastic cycles with full dynamics, right? Where is she? Yeah, yeah. So it is possible. So ask her. I think there's some other groups trying to work on that too. Yeah.
Next question. Yes.
Thanks a lot for the talk. My questions might be a bit naive because I'm not an expert in there. When we do the Bayesian slip inversions, that's just a comment, we definitely reached the 100 million valuations. We're running big NCMC stuff with thousands of parameters. So
Yeah, but that's for an inverse problem.
yeah, but
Yes.
when we're running the forward problem every time,
I
do it every million times. So
Yeah, I do know that, but I would say that if you're going to use this for an inverse problem, it would be different. Like this is a calculation for, how can I say this? Yeah, you're saying that you would need something to do a bunch of forward runs for a Bayesian inversion. I could see that actually being helpful, but I would say also that if you're going to do an inversion at all, and you're going to use a neural net, like a pin, for example, then just use the pin for the inverse problem. Don't do the Bayesian stuff.
well, except that Bayesian stuff gives you the maps the uncertainties from the data into the model as well.
So you want some uncertainty.
Yeah.
Yeah, no, that's totally fair. I also want that.
Another thing is that you were saying that the convergence is oscillating and not satisfying in the end. But that's also based on the fact that, as you said, every time we train these neural networks, we don't have the right architecture. And so unless you find the right architecture, which will probably very much look like the forward model in the end, you'll never reach the right convergence. So is there, I saw that there's new neurons that are developed all the time. Have you explored
Like other architectures?
other stuff like this diffusion stuff?
Yeah, no, there's like is it the deep O-nets? Like there's the neural ODEs that sort of pull in physics into the architecture itself, and I have not worked on those. Yeah.
Fabio?
Hi, thank you for the great talk. I was really exciting the possibility to fit the A-B profile so quickly. After the first run, it was already there. How difficult do you think will be to adapt this to real subduction zones, for example? Yesterday we saw several images with different patches. These patches can be large or small, and while you have this straight profile. Is it difficult to do this step or not?
I guess the way I would set it up is I would set up a three-dimensional problem. You have, you give your fault geometry, and I think it would, I would know how to set it up. In terms of how difficult it would be, I think the difficulty would come from how expensive it is to train a 3D problem like that, and how well you can like resolve things happening around the interface with the pin. So yeah, I would be most worried about the cost probably because it is expensive.
Can you clarify this point? It's in your point that are you assuming correct initial conditions, or you assuming you know initial conditions, or you're inviting for initial conditions?
In the pin stuff, yeah. In the pin stuff, we make an assumption of an initial condition. You can infer for it though.
Which I thought it was challenging.
I've never done it myself, trying to infer initial conditions, but it is possible.
Okay.
Yeah.
Alice and.
Okay. Great talking to you. Quick question: could you comment on extrapolation? Because that is just in terms of your.
So extrapolation to.
In the sense of using the trained models to extrapolate to ranges of parameter space that are not part of the trained.
Yeah.
Because that is something that I should go in here, and it's also very interesting.
It should go in here, yeah. I don't know how well they extrapolate. Yeah, sorry.
No, no.
It's more work. It's more work that needs to be done. I know. I'll tack that onto my to-do list.
That's good. Thanks.
All right, we'll take one more question. Can the next speaker start saying things up?
Excellent talk, thank you very much. I have several questions regarding the imposedness of the astroplastic problem, regarding the local minima for the inversion problem, but I have another one that I find it more interesting maybe. You know our problems here with discontinuities, heterogeneities.
Sorry, can you start that one sentence over again?
Yeah, our problems here with discontinuities, heterogeneities, so neural networks are considered as universal approximators under some specific conditions of regularity. For example, they might be bounded to regularity of our fields, which is not the case when we have discontinuities in our problem. So I would like to have your.
Do you mean like
thoughts about
discontinuities in like material properties or something?
yes, or even faults. Faults is discontinuity. So the U field is a Heaviside function, it's not an L2.
Yeah.
So I was wondering how far can we go by using these methods without taking into account this kind of non-regularities and non-smoothness of our fields?
I mean, that's another thing to add to the to-do list, but I mean, it's worth looking into just because like neural networks don't suffer from the same challenges as traditional methods in terms of dealing with discontinuities. So if you have, if you have like a discontinuity in a material property, right, that's really hard to account for in a stable way in a traditional method. And the machine learning, the pins don't have that problem, but I don't know how well they would do it.
Yes, because behind there, the proofs are based on irregularity, if I remember well, for the neural network. So if the functional space is not enough for
yeah, you might not have enough complexity in your neural network architecture to get that. Yeah, definitely possible.
Okay, great. Let's thank you. The next speaker is using the mic. Yep. Excuse me. Can I take this phone?
What's that?
The mic.
Oh yeah.
Thank you. Thanks. Can you hear me?
So the next speaker is Corentin Noël. He will discuss the role of heterogeneity, frictional heterogeneities on seismic cycles. Go ahead.
Can you hear me clean? Okay. So yeah, I'm going to present you an experimental work that has been done at GeoAzure on frictional heterogeneities. So the seismic cycle can be cut in different phases. This is a simplified representation of what happened at depth, and you have the slip here, and you have the time here. So during the interseismic phase, you have some section of the fault that are creeping, and some section, as you can see here, that are stuck, and they do accumulate stress over time. Okay. They do accumulate stress over time, and once you reach a critical stress, then you can start to nucleate an event, so you start to slip, and if you reach a critical length on this nucleation patch, you can have a large slip that occurs very rapidly, so you have a coseismic event during which you have an earthquake. On this diagram, you can see that still you have part of the fault that have a slip deficit, and this slip deficit is recovered afterward during a post-seismic phase. And today I'm going to focus among all the different post-seismic deformation you can have on post-seismic after slip. So they occur after a large seismic event. They can have a coseismic slip that is as big as the coseismic, post-seismic slip that is as big as the coseismic slip. And the location of this after slip is around the coseismic rupture. And there's different mechanisms that are evoked in the literature to have this after slip. So you can have stress heterogeneity, homogeneous fluid pressure distribution, and today I'm going to mainly focus on frictional heterogeneity. Why that? Because it's the main evoke mechanism in the literature, and it requires very simple conditions, just a velocity strengthening patch that is adjacent to a coseismic rupture. And I will try to answer this question. So can we have after slip in the laboratory just by adding simple heterogeneity, frictional heterogeneities? So we designed those samples in the lab. So you have faults, so they are 4 centimeter diameter, and they are composed of granite and marble. So we choose those two lithology because granite produces seismicity in the lab, so you have stick slips, and marble in the condition we tested is creeping, so it's seismic. And we have this marble embedded into granite and granite embedded into marble, and we tested different fault composition that are schematized here. So you have granite fault to marble fault, and so when it's white it's marble, and when it's gray it's granite. And I will use those schematic along the talk to show you which fault I'm studying. So we take those samples, we did a triaxial deformation, so we use this apparatus that is at Geological. This is a zoom of the sample that is in the jacket with all the sensors. So you have our sample here, the fault is here at 30 degrees from the axial stress, and all is set into confining oil so that we pressurize to put confining pressure on our sample. Our sample are equipped with the sensors, so today I'm going to discuss strain gauge data. So we have strain gauge that are close to the fault, and they measure the local strain, and they are, in our case, parallel to sigma 1. So what we did is that we kept constant, so that you have the pressure as function of time that we apply on our sample, and we put confining pressure of 30 MPa, and then we deform actually our sample, and we produce some seismic cycles. Then we increase the confining pressure to 60 MPa, produce some seismic cycle, 90 MPa, and then we went back to 60 and 30 MPa. So during the talk, I will mainly discuss this increasing confining pressure, the effect of this increasing confining pressure, and at the end, a bit of this decrease. So very briefly, so Chris showed that slide yesterday. So I'm showing you here the shear stress on your fault as function of time. This is macroscopically measured. So this is the granite fault, and it produced stick slip as expected, and the amplitude of the stick slip increased with the confining pressure. On the other hand, you have the marble fault that is creeping at all the tested confining pressure. And then this is the marble asperity, so you have a seismic behavior, but the amplitude of the events are much smaller than for the granite fault. Then the granite asperity into the marble, still seismic behavior, but again, smaller amplitude of stick slip. And finally, the bimaterial fault, still seismic behavior, but the smallest amplitude of stress drops. So the higher the confining pressure, the higher is the stress drops, and it seems that the higher the marble content, the lower is the amplitude of stress drops. So what about the local strain? So the interest of today, of this talk. So this is the strain gauge data for one seismic cycles. So you have 8 strain gauges, so it's the inelastic stress strain, so it's corrected from the elasticity as function of time. And for simplicity, I will present you 2 strain gauges that are the orange and the blue one that were selected because usually they have the smallest and the largest coseismic strain drops. So for the granite fault, so you can see that on the blue strain gauges, you have first a departure from elasticity, so you start to unlock your fault close to this zone, and then you have a macroscopic strain drop, that occur on both strain gauges, actually on all the strain gauges at the same time. So all the strain gauges record the fast strain drops. When you have a marble asperity, you have this departure of elasticity, then a fast strain drop at the orange strain gauges, but on the blue one, you have an increase of the strain, so that means that this part of the fault accumulates strain, so it's not slipping. But when this coseismic strain drop occur, it also record coseismic fast strain drops. Now the interesting part, so the marble, the granite asperity into the marble. So you have a fast strain drop at the orange strain gauges, but on the other side of the fault at the blue strain gauges, you have a large increase of strain, and then a very long-term decay that occurs over a few seconds. And finally, for the B-material experiment, you have similar behavior, so fast strain drop at the orange strain gauge, and on the other side, a very large strain increase, and then a very slow strain decay. So it seems that fast and spatially extended strain drops occur in grain-grade contact, and in the marble, it seems that the deformation is accumulated afterwards through a long-term decay. So this is what I will call from now on after slip. Very briefly, if you look at all the strain gauges, you can see that the fast co-seismic strain drop occur very locally around these strain gauges, and all the other strain gauges record after slip. So it seems that similarly to what is observed on natural seismicity, co-seismic and post-seismic deformation are released separated both in time and also in space. So let's focus. I will focus now a bit on this data on the after slip. So here I'm showing you the post-seismic strain accumulated as function of time during a post-seismic event. And you can see that so the post-seismic strain increase more or less log linearly with the time. And we try to fit our experimental data with these rate and state approximations. So it simply states that the strain accumulates over time depending on two parameters. So our initial strain rate, so the strain rate at the onset of post-seismic deformation, and the critical time, T0, that is a function of the normal stress on our fault, the apparent rate and state parameter A minus B, and some elastic constant that we measure in the lab. We also measure the normal stress on our fault, so basically we measure more or less everything except A minus B. So if we try to fit those data with this equation, we obtain a pretty good fit. So we are really pretty satisfied with this equation to fit our data. And if we retrieve our A minus B using the T0 that we inverted, this is what we obtain. So you have A minus B as function of the post-seismic strain, total post-seismic strain, and the color bar is the normal stress. So what you can see is that the apparent A minus B increases with both the normal stress and the post-seismic strain. And this increase in A minus B is very similar to what is observed for calcite gouge. So we have very similar value of A minus B, so we are pretty confident on our apparent value that are in the proper order of magnitude. And then, so this is what happened when you increase the confining pressure during the experiment. But what happens if you decrease the confining pressure? Do you return to that slope? The answer is no. So what happened is that our A minus B, inverted A minus B, remain more or less constant. So it seems that the fault keep in memory what happened in the highest confining pressure. And now the post-seismic strain is only dependent on the normal strain, on the normal stress. And what is interesting also is that if you multiply this apparent A minus B by the normal stress, you are able to align your point on a single line, let's say. And it means that the total post-seismic amplitude scales with the normal stress multiplied by this apparent A minus B. So as a conclusion, this is the first evidence, at least in triaxial experiment, of a large afterslip on a socket interface. We saw that afterslip can emerge from simple frictional heterogeneities. It is well explained by the rate and state theory. And importantly, large afterslip is favored by large normal stress multiplied by this apparent A minus B. Thanks for your attention.
Yeah, very interesting result. Since I'm the chair, I'm going to ask first question.
You're the right postdoc.
Feel like postdoc. Sorry, could you clarify what's the slip rate during seismic slip exactly? Is it a meter per second,
So-
0.1 meter per second? Is dynamic weakening happening?
So the recording rate is not enough to measure it on axis when it's very fast, especially for the grain-grain contact. So we record at a bit more than 2 kilohertz, the strain gauge data, and basically it's 1 point, 2 points, the coseismic strain drops during the event.
So even that
So I don't know. The answer is more than what we can do, and if I remember well, is 180 meter per second. Is it correct? I don't remember the exact answer. I can check after.
Any other questions?
It's a bit intriguing, this graph, because you seem to show that your parameters depend on the strain. So does it mean that the rock already knows what the strain will be? I mean, I can't wrap my head around this idea that these frictional parameters, which should be constant, depend on the actual final strain that you have.
So this is
Yeah, I don't really get that.
this strain I plotted here is like this value, like the when it plateaus, it's like the final. But now it's time, but it's the strain that the total amount that we accumulated during the post-seismic phase at this strain gauge. So it's just the measured value. So it means that to have like a large amplitude, you need a high normal stress and high A minus B.
But it means that every time you do a new experiment, A minus B is changing along. You say that's that. I don't understand the way you interpret that plot. And then this is the data, right? But what does that mean? That it keeps changing? If you have more post-seismic, it means A minus B was larger. That's what you imply.
Yeah, but I mean, for one condition, usually it's the same. Like, this is one of the conditions. So it remains more or less constant. This is one sample at 60 MPa of confining pressure. So the average value is around here, so 0.008. And then to change it, you need to change the conditions.
Well, I sort of had the question along the same vein, but maybe connected to something, well, evolution of the fault surface with strain. Could that be physics behind the fact that your apparent A minus B is evolving with strain?
So with strain, it does. For example,
Like you accumulating gouge or something?
yeah. So for example, the first event are usually here, and the last event are usually here. First here, last here. So there's a small dependence also on the strain. And if I think yeah. So on the sample at the end of the experiment, this is the picture of the sample at the end of the experiments. So some of them do have accumulation of gouge. So for sure you change the frictional property of your surface because you accumulate gouge or you create mirror surfaces and so on.
Okay.
Chris and Laurent, but Chris, sir.
Oh, thank you. Yeah, really nice talk. Just following up on that point, because I think the way you're plotting it, by combining normal stress and A minus B, is maybe a little bit confusing about the question, especially that Nicholas asked, because it doesn't really look like A minus B depends on strain in any particular way, or maybe just through the little bit of wear that you have in your experiments, right? So in any given experiment, there's a small variation in A minus B as a function of strain, but it's not the major effect.
Yeah.
But it accumulates over many tests.
Depends on, between tests you start with a new sample, right?
No, like they all experience an increasing confining pressure and then a decrease.
That's right. Yeah.
But yeah, this plot means like if you want in nature to have large after sleep, you need or very large normal stress or very large A minus B, or a combination of both.
But especially for shallow afterslip, the normal stress is probably not very big, so it's
Yeah.
A minus B.
Or a lot of post-seismic strain, or previous strain or sleep.
Yeah.
Laurent?
Really quick, why didn't you do, on both sides, the crown of disparity surrounded by marble, like a little repeating earthquake, maybe?
Like the asperity that is symmetric.
Yeah.
So two reasons for that. First reason is that we wanted to have the strain gauge on a simple material because initially we wanted to do more inversion. So we wanted to have a simple half sample at least, because we don't exactly know what happened at this at the junction here. Like maybe there's a small crack, so it may influence the data. And second is also when you shear, so you have your two folds that are moving on this configuration, so the asperity is shrinking also with slip. So we didn't want it. We wanted to have the same size of asperity during the entire experiment.
I just thought that would be interesting, but
Yeah.
I can see the practical issues. Yeah.
While Sylvan's asking question, Yifan, can you say something? Yeah.
Corentin, can you, did you try if the after slip that you see can be explained on a log-log plot forming a straight line, or if it's truly log linear? Can you resolve the time scales that create, different time scales that resolve if it's log linear or power law as you can?
I don't have the backup, but yes, we did. So we have a, if I remember well, it's not exactly linear. Nothing to do with that figure. Not exactly linear, but it's like there's a small acceleration and then a straight line. On like to plot this on a log-log. Yeah, it does this and then a tiny bit of this.
Yeah, so it is a power law with an initial condition.
Yes.
Yeah.
Or an acceleration conditions, I don't know.
All right, let's thank the speaker again.
If you want to use the pointer, it's there on this one, as you want.
Let's see. How does this work? All right. Okay, maybe I just use the.
Put that in your pocket.
Okay.
Yeah, so the final presentation of this morning will be given by Yifan Yin. The title is Stress Test, Earthquake Cycles under Different Loading Conditions.
All right. Okay, hi, I'm Yifan. I'm currently a postdoc at MIT working with Camila on how to actually stress your fault in a earthquake cycle simulation. So before I dropped down the rabbit hole of earthquake cycle simulation, I was a seismologist. And why I got trapped into this hole is that when you look at these like maps, it's very impressive that you have well-mapped fault and major sequence. And what if you can just put that in a simulation and churn, and then it could output possible earthquake clustering, possible stress evolution, and possible like a hazard, right? But this is like really huge. So maybe we can like scale down a bit, and this is the displacement for Ridgecrest earthquake. Because see, like even for individual earthquake, it's still very complicated. There are brands and there are roughness inside. But however, we can still extract the major features and put it in a box, right? Okay, we put it in a box, and now we ask ourselves, what does the fault actually feel? So it can feel the tectonic stress that's shearing it. It can feel maybe post-seismic relaxation working against the tectonic stress. It can feel the creep, like if it has like a seismic parts outside the seismogenic parts. It can have roughness onto itself, or it can have a fault that's like pushed against it. And why do we need to think like how a fault feels? Because it's actually the stress heterogeneity is actually quite important for all these topics that we care about. For example, how roughness initiate, nucleate, and finally initiate the main shock, and how rupture jumps from one planar fault to the other fault if it has a restraining or releasing band in between them, or how does earthquakes cluster if it has like multiple faults interacting with each other. And apparently the stress state also affect the friction too. So we want to know about maybe the stress heterogeneity and how strong it is. Okay, so this is my favorite, second favorite geometry. We have a fault in a 2D full space. Now, because in boundary element models, we don't have actual, like a box. So instead, when we want to shear this fault, we just say, okay, the shear stress on this fault is some initial value plus a fixed value that continue increasing over time. So over time, you'll have a stress that's this big. It's like flat across the fault. And as an earthquake happens, it will release the stress you give, and it will create this elliptical slip profiles. That's just the profile of a crack of constant stress drop. It's in the textbook. Yes. Now you could also, instead of giving it a constant slip rate, so when you say you need to slip at a constant slip, it really just means that when your fault patch is not slipping at a designated slip rate, and it will create stress interaction. So when you do this, it's really equivalent of saying that, okay, there's creep outside your main fault that is stressing the inside. So it's exactly the same. And this is the stress that you will give when you have this kind of stressing. So you will have a very sharp stress when the velocity is different. And when you slip at the same rate, it will practically have no stress. And this is the output slip profiles with this stressing function. You'll have just a flat. So all points on your fault will slip at the same rate. So it's just a summary. And this is all good. But what about when you have two faults? Or when you have rough faults? So when you have more than one fault and it's not planar, the slip on one fault will generate normal stress change on the other fault, well, in addition to the shear stress that it imposed. And this will keep accumulating. So now, which one do you think is better? So the fact that is that actually they are like both good and bad with all this method. So for example, if you shear it at a constant stressing rate, your stress and slip really conserve across the fault, and there will be no excessive slip. But then it's hard to compare your slip rate with the geological records, and the stress could accumulate. But if you use this kind of stressing method, you could just use the field measurement, and the stress will not explode, which is pretty nice for like long-term earthquake cycle simulations. And however, it does not preserve stress interaction, and I will show it later. And the excessive slip will so because you stress it at a constant slip rate, so the slip rate will actually double at the overlap. So how do we proceed from here if we want to really run like a more complex simulations? We really want to, first of all, we want to preserve the stress heterogeneity in this fault system, right? If we want to know the hazard or predictive model. And we also want to keep track of stress heterogeneity and without our model go explode. And finally, we wonder if we can actually estimate the range of stress that's in like a different complex system, and maybe we could link it with geology and friction. So let's do some numerical experiments with everyone's favorite friction law. So this will be exactly the same, say very classic. And I'll use my favorite geometry, and we run our simulation in Bedrock. And what is done differently is inside the stress. So normal stress here and shear stress here. So in the following, I'll use 3 different loading method. The first is a constant stressing rate, and the second is constant slip rate, as I stated before. And the third one, we try to add another term that relaxes the stress as the stress accumulating. And the rate of stress relaxation is simply determined by the difference between the stress and the initial value, like divided by the relaxation time. And the relaxation time can be the actual viscosity, but it does not necessarily need to be it. And it's just like a parameter you could turn. And you could see the effect that if you add this term, you'll have stress. So this is a stress accumulated at the restraining band. But if you add a relaxation, and you could reach a long-term steady state, like after a lot of cycles. And this is also not new. A lot of the papers have done this using this kind of simple relaxation. Right, so it's just a recap, and well, you could see how different loading actually make your simulation look different with just one fault. So this is just this is the location on the fault, and this is just the slip rate plot against time step. And then at the middle is the slip profiles. So if you load it at a constant stress, you would see that your slip profile remains elliptical and throughout your simulations. But with constant stressing rate, you'll have a more or less flat profile, which you can see interseismic loading at the top and bottom. And they output slightly different recurrence time too. Okay, now this is my favorite geometry, which I turned it 90 degrees sideways to show you the velocity evolution on each of the faults. And this is just with constant stressing. So the stress continue to accumulate. And you can see the seismic sequence start out pretty stable. It's always a full rupture on both faults, until at some time you start to have partial rupture here. And seismicity turned to pretty irregular. However, you can see this is the average slip rate on the fault, and it actually remains a more or less elliptical profile with overlapping between forms of like bigger elliptics. Now, this is so next we check the stress profile and the slip rate profiles on the nucleation point of two faults. So at the bottom, I showed the normal stress on that point and shear stress below. Then you can see the normal stress just keeps decreasing until at a certain point the normal stress, well, the stress difference is large enough that it starts to give like partial ruptures. And you can see that when the stress continues to change, then you'll have a non-stationary earthquake sequence. In this case, it ruptures faster and faster, and the two faults start to get out of sync.
Is it shear stress or normal stress?
This is normal stress. This is shear stress. Yeah. So what if I use a constant slip rate? The first thing you'll notice that the rupture just start to get very irregular right from the start. So with very little interaction, it could actually give you a partial rupture that actually resembles a real catalog. You also notice because the stressing rate is largest at the boundaries, it always starts from the boundary and rupture inside. And you just have full ruptures up and down. So yeah. And the problem with this method is that yes, it has flat slip profiles on the same fault, but if you have overlap, you will double the slip rate. And this is the same, the slip, the velocity profile and the stress profile. And I marked the full rupture up here. And it's like a semi-regular recurrence for the full ruptures, but they have a pretty large variance. And what is good and bad about like a constant slip rate is that it will actually control your normal stress in sample. Really, really, really close to the initial value. So what it means is that it really cancels out the fault interactions.
2 more minutes.
Whoa, okay. So, so yeah, so this is just a cross section of the slip profiles. The blue one is normal stress, and you can see that this is where the earthquake nucleate at where the normal stress decrease. Notice the shape of the profile, and this is when you have constant slip rate. The normal stress profile stays pretty flat, and so is the shear stress profile. So what is being irregular here is really your slip rate field, and it's where it nucleates. Okay, so what if we add a bit of relaxation? And because we add a pretty strong nucleation, so the simulation does not reach the stage where it starts to have partial rupture. So it stays really regular throughout. But you can see how relaxation really like modulates the degree of stress increase and decrease in the stress profiles. So this one is with really long relaxation time, about let's say 10 times the cycle length, and this is with 1/10 of the, I think 1/3 of the cycle length, and the stress returns to normal during the interseismic times. So what's good about this method is that it's actually really simple. So when it reaches the steady state, we can actually calculate how far the long-term stress is from the initial, our initial values, just by like figuring out the math here. And it gives out a really simple like one-to-one relation that says, for example, if your relaxation time is 3 times your seismic cycle length, then it roughly remembers like the stress from 3 earthquakes before. So if we think about it, we can sort of like gauge what could be like the stress heterogeneity, for example, inside a region like this, for example. Like if you have a relaxation time of 50 years and your average recurrence time is 20 years, then you can probably say, okay, the stress heterogeneity on different faults can be calculated as like 2 or 3 times the Coulomb stress change from like earthquake before. Okay, so these are my conclusion. I hope you are convinced that loading your fault differently really creates different results for your simulations. And there are like 2 points I would like to discuss. The first is, when I use the different loading method, the complex sequence really go away. So what actually gives rise to the complex sequence? Maybe roughness or other heterogeneity on the fault. And another thing is that, can we like speculate on the scale of relaxation time? Maybe we can chaining multiple relaxation time from different physics, and so far it's just a knob to turn, but we would like to link it to geology. So thank you for your attention.
Thank you. Time for questions? Students, postdoc. Okay. Postdoc Sivan.
Yeah. Great talk. Thank you.
Thank you.
So I felt there's maybe one geometry that you
Yes.
may have overlooked. because VL in your model is simply the long-term slip rate,
Yes.
as you show in your calculation. So if you have overlap between structures, typically you have a reduction of the long-term slip rate on
Yes.
the overlapping structure. And so you can simply consider a tapered long-term slip rate. Instead of choosing one uniformly for each fault, you can make them go down when they intersect in a tapered fashion, and then it will satisfy your long-term slip rate for the plate boundary.
Yeah, you could do that, yes. Yeah, that's one way to do it. I could actually mimic the elliptical profile, and it would give me like the perfect elliptical ruptures, and also reducing the stress. I guess my problem is that the stress interaction is not preserved. However, you use the slip boundary conditions, so that if the Coulomb stress are there, then it should be there in the model. But if you're constantly like subtracting the normal stress imposed on the other fault, then like the information is somehow lost for me.
Yes, I don't quite understand what this viscous relaxation represents in reality, because after an earthquake you have viscous relaxation, which is actually reloading the fault, right? Here you have a stress which is reducing with time. So in reality it would be an elastic deformation in the belt that would avoid the elastic stresses outside the fault to explode. So can you comment on that?
So this is like a convenient way of doing that, and the previous papers say that it's like so it will behavior will be the behavior of a inelastic block, incompressible block. So this is just 1D Maxwell relaxation, and this approximation is like good enough for in the starting of the relaxation. And because we are doing boundary element simulation, we're not outputting the displacement, so we kind of get away of just using this.
So is this term representing damage in the block that relaxes the stresses?
It can be a lot of things. So far I linked it, for example, when I choose my parameters, I linked it with just viscosity, or for example, lower crust. And I think it can be the composition, like the stacking a lot of different relaxation mechanisms together. So it's still.
If it were the lower crust, it would augment the stress.
Not
relax the stress. So we would have to represent the deformation of the block at the seismic depth.
Thanks for the interesting talk. So you showed the map of many faults in California, which appear finite along strike, right?
Yes.
So what is the sense of using this the slip rate at the end of imposed on at the ends of the along strike of these finite faults and a system of faults on top of it? What it has to do with how these faults are actually physically loaded. I mean, maybe they're loaded by dislocation if you consider the 3D nature through the roots, but
like idea of constant slip rate really, I think it really comes from the subduction zone. As you see from the talk before, the subduction zone simulation is always loaded by constant slip rate. I think it can come from there, but then it got quite handy when people are simulating using earthquake simulators. That's also briefly introduced. That
but how can you put it in a framework with many finite faults?
So that's also my confusion with it. So, but then we still probably need some relaxations, some way to relax the stress if we want to continue with simulation. So this is one way to do it. You could also just use volumetric method to simulate a bunch of faults, but it will be quite expensive.
So when you are using slip, I think with the overhead info is kind of unfair because you show yourself that it's pre-allowed to put the stress concentration at every tip of the fault. But what you could do is just put a stress concentration to the far left on the fault that is on the left.
Yeah.
The same stress concentration problem of the normal traction that is not building up between the two interaction fault, and also the slip rate, long-term slip rate will be followed by the